I did it again, everybody. I did it again. I was talking to everybody and no one could see me. I did it again. It's that second sip of Red Bull. We just went live right now. But I was like, hey, who knows the answer to the question? No one knew it. There was no responses. I know, right, Sylvia? So I just hit live right away. I was just watching like the intro music and I was like, hey, everybody, how are we doing? Went through the intro music, went through everything. So we're now here. We're now live. I know, right, Brennan? It's that second sip of Red Bull. I was talking about Rockstar. And I asked a question. I said, you ready? Here's the question I asked. The question I asked was, who knows the three conditions in Stat 201 we use for regression? Who knows the three conditions we use in Stat 201? So I always start out by asking a question, make sure I'm live. And it looks like I am live right now. Who knows the three conditions in Stat 201 we use for regression? We're jumping right into it. I lost 1 minute because I didn't hit that go live button. Dennis, you get 1,000 points. Dennis is right for the three conditions in 320. Now, don't write down what Dennis has. Write down what Dennis has because that's what you should know for your test. Dennis is right for the test. Who knows? I think StreamYard is probably still waking up since I just hit the go live button. QQ, straight enough, no outliers. Then you get 1,000 right here. We're starting off strong right here, waking everyone up. Brian's awake, Red Bull's awake, and Red Bull's obviously awake. And so in Stats 101, it was QQ, straight enough, no outliers. And then the fourth one is plot doesn't thicken, which is the equal spread. And Dennis points out the ones we have in 320, which are normality of residuals, which means they follow the bell-shaped normal curve pattern looked at by a QQ plot. Equal spread, which means we see homoscedasticity, the same thickness throughout. And linearity, which means a straight line well approximates the relationship of the points. And this is seen in the first plot. Very important we know this, that when we look at this, I think we've got... We'll go all the way back here to multiple regression part 1. Where's multiple regression part 1? Here it is. So multiple regression part 1 right here, we did normality of residuals. And here's the linearity. So the linearity says that line in the middle goes down it. And you can see it like in this first plot right here. Here's the linearity of the whole model. And here's the linearity of the individual variables. And then these plots right here test for the normality of the residuals. We mainly look at the QQ plot for normality. But why is Brian bringing up QQ straight enough, no outliers? Because today we break one condition. 1,000 points. What condition are we breaking? Be quick on the keyboard, first person. What condition are we breaking? What condition are we breaking? James is right. We're going to break the QQ condition. And now I say that. I say we're going to break the QQ condition, but we're actually not going to break it. Because I'm like, it has to be QQ straight enough and outliers, but we're actually not going to break it. And there's going to be a trick. There's going to be a trick you'll see. So we'll have a trick to make categorical variables quantitative. And you're like, how can you make a categorical variable? That's impossible, Brian. No, anything is possible. Let's take a look at this right here and see what we would do. Motivation, gender discrimination. So we're actually going to look at the Harris Bank court case. This is something I alluded to earlier. This is a very famous court case that took place, I think, through the late 70s, through the 1980s, and a real bank in Chicago. There was gender and race discrimination in their salaries, and they were able to show it. There was millions of dollars of settlement. So real data right here. And let's take a look at it. So this goes back to yesterday's lecture with multiple variables. We have here education, experience, months, education, experience. And so it's important to know how to interpret coefficients like this, such that we see people with higher education. When education is higher, the impact on salary of experience will be what? For higher levels of education, the impact of experience on salary will be what? For higher levels of education, the impact of experience on salary will be water. See, I can't have you guys write this out. I wish I could. Because it shows you can interpret the interaction to say, for higher levels of education, the impact of experience on salary will be water. Lower, weaker, exactly, Brad, 100 points right there, you're right. Because it's going to take this coefficient and make it weaker. Like every time education goes up, the coefficient of experience will go down. Does that make sense right there? And it'll go towards 0 probably. We can look at the implicit lines plots and that'll show what's going on, like we can actually visualize it. But if you just think, imagine if you plug in 0 for education right here, what would be the coefficient of experience? This is a question from last night. If you plug in 0 for education, what's the coefficient of experience? If you plug in 0 for education, you'd put 0 here. That'd be 0 times 0 times this. So what would be the coefficient for experience then? But 0, not 1. You might be thinking of 1. Good job right there, Ryan. 100 points. You might be thinking of 1. If you plug in 1, it'd be that. If you plug in 0 for education, the coefficient of experience would be what? Worried about last night's assignment now. Might have to draw this out. If you plug in, I am going to draw this out. Let's draw it out. So, what we have right here is the equation. I'm going to do a little shorthand on the equation right here. And we're predicting salary. But 0, if we plug in 0. So we have salary. We're just going to call it sal equals 2660. I'm going to abbreviate all decimals. Plus 144 ed plus 34, we're just going to round, experience, and that darn months right there, plus 12 or 13, because we're going to round up, months, and I'm going to zoom out a little bit here, minus 5 times ed times experience. Okay, there is the equation. The equation right here, and it probably would have just been easier if I wrote it out. Let's write it out right here. You ready? So let's write it out. Salary equals 2660 plus, yes, you're seeing it now. People are typing the answer in the chat. Sometimes I forget I can write faster than I can draw with horrible handwriting. It's the morning, so my brain's like, can I write it or can I draw it? And so we see this right here. We'll make this bigger. Okay. So the point of this, and the reason I'll draw it in a second here. So the point of this right here is that we have the interaction term at the very end. And what we can do is we can plug in values for experience or education and talk about how it impacts the model. So when we plug in values, I think I was talking about education. If we plug in a value for education like 0, we would do the following. I should put a multiply there. So we'd plug in 0 for education, and then you would solve out the equation. So let's put that back here, and then let's put that there. So we're going to times this by 0, and this becomes 0, and I think we're good. So this right here is equation, we could just put when ed equals 0. So that is the line right here when education is equal to 0. Does that make sense to everybody what I just did? When education is equal to 0, this is the line we get. When education is equal to 1, you can go right here and plug in a 1, and that's just going to equal 1 times that. So we get that right there. When education is equal to 1 right here, you would get this, which that's 5 times 1 times EX right there, and you're just going to get this right here. So you combine like terms now. So this will become 29, and that's a rounded version. And then this is plus 144, so that's 2804. All I'm doing is adding up these two numbers right here. And that goes away now because we just added it on. And this is when education is equal to 1. Who thinks they're following me on this right here? Like, who's like, I understand how you're plugging in values for education and solving for these lines. And we can see here that experience is going down in its coefficient. That's what you need to see. We just wrote out the equation. So I used all of these coefficients here to write the equation. And then I'm just plugging in the values. A few people emailed about this last night. They're like, how do I solve the line? So I sent them basically this example with it plugged in. And that's why I definitely, with what people email me, I try to like focus in on that during lecture. I'm like, okay, it looks like we'll look in on that. We'll make sure people understand what's going on. Streamlabs, you awake now? Streamlabs, you got to wake up. I'm gonna load it in the background, make sure it's loaded. Did just give the points. Streamlabs, you're awesome. Does it make a difference whether the interaction is? Nope. It doesn't make a difference which way we write it. Either way, it's good. If it's education experience or experience education, it's both ways. Like the coefficient of experience depends on education. The coefficient of education depends on experience. So it doesn't matter which way it's kind of shown right here, but there's an interaction either way. Like the coefficient of so you could plug in. You could go right here, and you could do when experience is equal to 0. So you could go right here and just start plugging in and plug in 0 here. That's going to 0 that out. And we said experience is equal to 0, right? Yep. So this is the implicit line when experience is equal to 0. So you can do this. So you can get the line when experience is equal to 0. So and that's why there's 2 plots when you do it. It shows you lines like when experience is equal to this or education is equal to this. So this is when experience is equal to 0. And all I did was take and plug in values for that. Does that make sense there, Brad? You can do it either way. And the coefficient of education depends on experience. The coefficient of experience depends on education. So because there's an interaction, like those two variables interact. Yep. Great questions. 1,000 points, Brad. Keep up those great questions. You got it. Chapter 5. So that is the interactions, and it just means that one variable's coefficient depends on another variable. Let's hop back to the big screen. Okay. And so the coefficient of education for salary, because it's how education explains salary, depends on experience. Remember, once again, the way in which x1 impacts y depends on x2. That's how we interpret an interaction. You can call this x1. The way in which x1 impacts y depends on x2. So the coefficient of experience predicting salary depends on education, or you could do it this way. The coefficient of education predicting salary depends on experience, and this is how it changes it. These are going to get weaker as the other one goes up. So whichever way you use it to do the interaction, it will make them weaker. I guess technically once they go negative, they could get stronger because they'll get like weaker, and then they'll like start getting stronger again. So weaker, stronger, it's just more negative. And so there's the lines, once again in the notes for us to see. And months interactions. We don't have interactions on the months. The months is going to be constant. So there's no interaction on the month variable. There's just constant because the month, you can see, does month have a constant effect? Kind of a very quick and easy test question to ask. Does months have a constant effect? Like why, if this was a written question, why would you say the impact of months on salary has a constant impact, has like a consistent same impact? Why does the impact of months on salary have a consistent impact? Why is it kind of the same impact at all times? Like two people who differ by 1 month are expected to differ by 12.7 monthly dollars in their salary, where the person who's worked there longer is expected to have more monthly pay. Why is that kind of the same no matter what? No matter the other variables. There's the hint. No matter the other variables, months has the same impact on the model. Why would that be? Who knows? Red Bull knows. 100 points, who knows? Up to 500 points today, unless you get the 1,000. Big points today. So, education experience. It's one of the independent variables. That is a true statement, Brennan. That is a true statement. But education is an independent variable, but education does not have a constant impact. Education, not the amount of uncertainty. It does have a relatively low amount of uncertainty, because if you notice, so why does months have a constant impact, but education and experience do not have constant impact? Education and experience do not have constant impacts, but months, you're over 10,000, yes. Months, that was my goal. If you're here, I want you guys to get over 10,000. That's what was my goal with this semester. I was like, I gotta just start giving out big points, because 10,000 is the big limit. Education and experience do not have constant impact. Boom, Grant, 100 points right there. Grant is right. There's no interaction on month. That's why months has a constant impact. Months is the same irregardless of the other variables, where education and experience have their interaction. So education and experience are not going to have a constant impact. They are going to be dependent on the other one. So you can't say it's always this difference. Does that make sense? You can't say, oh, two people who differ by this amount are expected to, two people who differ in their education by 1 year are expected to differ by this. Well, that coefficient right here, that coefficient right there depends on experience. So this coefficient here, I think I can highlight them both, depends on what someone's experience is. If someone has a lot of experience, then that coefficient is going to go down. So we have to be careful in interpreting those coefficients because it depends on what someone's experience is, the education coefficient. Be very careful. So once again, there is no interaction. That's what these slides say. Once again, if you're wondering, I always say what every slide says. You can read the slides or we can talk about them. And so there's a big gap in gender right here. So here's the thing though. Like you have to watch out though, because in regression, we want to control sources of variation. We want to understand where the variation comes from. And you can see there is a big gap in monthly salaries between males and females. The gap in monthly salaries is $545. No, my brain is way off. Oh, wait a minute. Yeah, it's $545, I think. Why not check? Why not check? Make sure that we're doing the right math. Between the means, oh, that's so much easier with the medians, $320 right there. So 3971 minus 3426, 545, 545. So we have a difference of $500 monthly, $545 between the males and the females. You might say, well, let's do this outlier. That outlier is not going to, well, it's going to maybe make this one higher, but the median's also higher. So somewhat symmetric, but a little bit, it's a little bit left skew actually, because it's pulled down in this direction from the median to the first quartile right there. This difference is statistically significant, meaning what? These differences are statistically significant. Explain to me what it means that the differences we observed on the averages between males and females or the medians between males and females. What does that mean? I said something way off here, 520. The tape in my mind is saying you interpreted that wrong. I think I was looking at another number. That's the difference of 520. The differences we observe between males and females between their means and medians. Who's going to say our favorite phrase? I'm going to do it. Who's going to say our favorite phrase? The differences we observe between males and females for their medians and means is what? 1,000 points. Favorite phrase. But you got to say the full thing. You can't just say the one word. Boom, Dennis. Unlikely by random chance right there. Getting everyone woken up. It's unlikely by random chance. Yeah, that's what the low p-value means. If it was a high p-value, then the differences would be likely by random chance. But the low p-value means this is unlikely by random chance. It means it's statistically significant. There's other ways of saying it too. Any low p-value below 0.05 is statistically significant, but then what does it mean in context of the problem? You can't just memorize low p-value, reject a test. There's things I know that people make mistakes on, and I'm not trying to make people fail the class, but I know the mistakes people make, because a lot of times we will look at output where we'll see low p-values here, and you'll be like, okay, fail the test, like we fail every one of these tests. Every one of these tests, we fail because the p-values are low. Then you go back to here, and you're like, oh, we failed the test. No. What we were looking at right here, the null for this, if you go to classical statistics, is that the means are equal. The null would be that males and females have an equal mean. So if you look right here, you would say that given the means are equal, the differences we observe for the males and females is unlikely by random chance. If you go to this example, the null is that linearity is good. And so the plot we observe over here for the linearity is unlikely to have happened by random chance, so we have evidence of nonlinearity. So you always have to think about what does it mean in context. You can't just look at a p-value and be like, aha, we failed the test. Yeah, that is true for that one. Aha, we failed the test. I mean, if you're saying the test is that they're equal, then yeah, you fail that test. I guess you could view it that way. Make sure you understand whenever you see a p-value what it means in context of what you're doing. It's always looking at your results. So what was my result right here? My result was the difference, and this difference right here was unlikely. This one is looking at the linearity. And so when we look at the linearity, this linearity was unlikely by random chance given that it's linear. And this difference was unlikely by random chance given that the difference is 0. Who feels like they understand p-values after this class? Give me some hype in the chat. Who feels like they're like, okay, I think I understand p-values a little bit better? Because just looking at your result, telling you if your result was unlikely by random chance. And then you have to be like, okay, what am I looking at? Nicole, 100 points right there. Good. It takes practice. You have to hear it a bunch of times, and you can't just be like, oh, every p-value means this. Philip and Emily, 100 points right there. Ben, 100 points. Yes, practice what it means. And you can't just be like, that p-value means reject. I mean, it does mean reject the null, but what does that mean? What does that mean? Well, we have other things that might explain the differences in people's salaries. It might be education experience, months on the job. There's a whole bunch of things that might explain it. Because take a look at this. These could be the lurking variables. Lurking variables are variables in the background that could be the variables that explain something. We've seen this early on with things like shark attacks and ice cream sales. Ice cream sales and shark attacks they're completely associated, but the lurking variable between ice cream sales and shark attacks is summer, because summer is, you might be like, how do you know it's summer? Well, it's pretty safe to say it's summer. I can't prove it, but if you control for time of the year, then we would see that ice cream sales and shark attacks are actually better explained by time of the year than they would be by each other. So the lurking variables here could be things like somebody's education, because we see here that, generally speaking, the males at the Harris Bank Company had a higher level of education. It could be experience. Interestingly enough, the females at the company had more experience, and also they had more months on the job. So you say, okay, it's probably education. I'm not saying that's what you're saying, but if someone were to say, maybe it's these variables right here, maybe it's these variables right here, that it's people's education that is actually explaining their salary. What do you do in a multiple regression to control for lurking variables? To control for lurking variables, what do you do in a multiple regression? To control for lurking variables, here's what I do in class. I go like that. What do you do in a multiple regression to control for lurking variables? You go, take those variables and do what with them? What do you do in a multiple regression to control for lurking variables? If someone says, I think it's actually due to this, someone's like, I don't think that's the real cause. I think it's due to this. You say, okay, let's take that variable and do what with it? You take that variable, you put it where? Should see it here in a second. Do I not show it? I will show it in a second. You take that variable, you just put it right in the model. So anytime someone says, maybe it's due to the education, the experience, the months, you take the variable and you put it in the model. If you say it's due to gender, you take that variable and you put it in the model. And just think about this. The mathematics of the model doesn't care. It doesn't care what you want to be significant. It's just going to do the mathematics. It's going to figure out what explains what. It's going to mathematically compute the best variables to explain and just literally solve an equation. That's all it does. And that's the thing I love about it. Math is just like, math's going to do what math's going to do. And so we'll go really fast forward in the notes. We'll go back through this. But you can see right here, what have we done? We have incorporated gender in the model. Now you might be wondering, wait a minute, that's gender male. Where's gender female? Well, let's show it right here. How are we doing this? How are we going to take and encode a categorical variable into the model? That's our issue right here, is that we have a categorical variable and we need to put it into regression. Well, here's how we do it. We put it to a quantitative variable. Remember how I said we're going to break QQ, but we're not going to break QQ? Here's how we broke it, but we didn't break it. So the variable right here will be a 1 or a 0. Now, there's an important key term you have to know, is we have what is called the reference level. The reference level, you need to remember this. I want to see this in chat for 100 points. I am first. I am first. This will help for the last 4 classes we have, the last major 4 classes, Thursday, Friday, Monday, Tuesday. I am first for 100 points chat. Boom, Alex. 1,000 points, Alex is first. Alex got 1,000 for being first. So I am first. Logistic last. I am first. Logistic last. Put the whole thing in the chat now. Remember this. I am first. Logistic last. I am first. Logistic last. Now, what does this mean? Because I'm already giving you the logistic last thing part here. With indicators, the reference level is the which one? With indicators, the reference level will be the what? With indicators, the reference level will be the what? With indicators, indicators, that's the I. First. First up, yeah. So if we had days of the week, which we can always do a multiple one, if we have days of the week, what would be the reference day of the week? What would be the reference day of the week? Who can tell me for 1,000 points what's the reference day of the week? Not the first day of the week. Friday, Philip is right. Why is Philip right? Everyone start decoding. Why is Philip right? Philip is right. Why is Philip right? Why is it Friday? Because that is first. First what? It's the F. Because that is first. I want to see in the chat, see if you're following along. F is first and first alphabetical. Boom. Mila right there, 100 points. How about freshman, sophomore, junior, senior? What is the reference level for freshman, sophomore, junior, senior? What is the reference level? And this, I wouldn't love this as a test question because it is freshman. But is that because freshman comes first? Like they're like the first thing you go through? Nope. It's freshman because it's first alphabetical. What is the reference level for winter, summer, fall, spring? What is the reference level for winter, summer, fall, spring? Fall. Fall comes first. What is the reference level for chocolate, strawberry, banana? Chocolate, strawberry, banana. What's the reference level? We say, okay, we got chocolate ice cream, strawberry ice cream, banana ice cream. Banana. Because B is first. No. No, like, yeah. It's B, banana. So this is how we figure out which one is the reference level. Who feels like they have it down to understand how to figure out which one's the reference level? If I give you multiple groups, the reference level, I know, right? It's good practice. It's like you get it down. You're like, okay, the reference level, I am first. And why do we memorize I am first? We memorize I am first because with indicators, the reference level is the first one. And we got more slides to show this off. I used a lot of the examples. If you have smile, yes or no, no comes first. So that's the reference level. If you have homeowner or renter, homeowner comes first. Put Alex is really great. Alex, you're at 2,000 points today. Alex is so good at putting test questions, and I'll have to write a lot of the tests this weekend. And you better believe I'm going to what Alex puts and just going through Alex's questions and being like, yeah, I can use that. Yeah, I can use that. So Alex has basically been building a study guide. And I think I've looked at them every once in a while, but go to the Discord. So hop on the Discord, start checking it out. And I'll probably be on the Discord some too. What if there's two things with the same first letter? Wow, Ben, 1,000 points. What if I have Ben Austin and Ben Folds in this class? What would be the reference level? Ben Austin, I mean, it's not really a level, but Ben Austin makes music and Ben Folds makes music. And we ask people, who do you listen to, Ben Austin or Ben Folds? So what would be the reference level? It'd be Ben Austin. You keep going through. Here's the good part. I'm not going to try to be too tricky on the test, but it'd be Ben Austin instead of Ben Folds. Technically, if Ben Folds decided to do this with his name, it might be Ben Folds then. Don't worry, the computer will figure it out for you. But if there's the same first letter, it then goes to the second, to the third, and it permutates through. So if we had like two artists, Ben Austin, Ben Folds, and we asked people, who's your favorite artist? We would then, the reference level for this would be Ben Austin. Because Ben Austin is first alphabetically before Ben Folds if you go through the letters. Does that make sense right there? That's a really good question. Yeah. I love it when you're following along. Smooth jams from Ben Folds. And so, yep. And so we see all these. And then we should mention, though, like you should be like, well, what's this reference level thing about? Well, think about this. Sorry. Here, we can delete your name, Ben. Sorry about that. I was just, if you want, I'm sorry. I didn't mean to freak you out right there, Ben. Sorry about that. And so with this right here, what does it mean for something to be the reference level? Okay, good. I didn't want to really freak you out. The reference level is what we're going to compare everything to. It's like in reference to it. So imagine, and I think this is an easy way to think about it. We're going to give away my family's ages right here. Okay, so what's the reference level for Brian's family? There's Brian, Darren, Emily, Patty, Dave, Tolliver, Everett. Yeah, I like it. Brian, Darren, Emily, Patty, Dave, Tolliver, Everett, What is, put Chelsea in there, Jessica, Brian, Darren. I've given it away. What's the reference level? What is the reference level? Brian, you're right. I'm the reference level. I am the reference level. Brian. Yep. Why is Brian the reference level? First alphabetical. So what's it mean for Brian to be the reference level? Okay. Brian is 38 years old. That's Brian. Darren has an age of that. What child am I in my family? Who knows what child I am in my family? So we got Brian's age here, and we got Brian's the reference level. And then Emily and Darren have coefficients of those. That's Emily's coefficient, Darren. I'm the middle child. There you go. You know the age of my siblings. So you can see right here that I'm the middle child because in reference to Brian, Darren is 2 years older. Does that make sense what a reference level is? It's like when you look at the other thing, here's how it is different from this. So why is this the reference? Why is Brian the reference? If you know Brian's age, then I can say Darren is 2 years older than Brian, and we're referencing Brian. That's why we're calling it like the reference level. So you'll see that in the regression that when Friday's if Friday's the reference and Saturday has a coefficient of 5, what does that mean Saturday is? If Saturday has a coefficient of 5, and this is where you'll really be getting it, if you can tell me since Saturday has a coefficient of 5, what does that mean about Saturday? If Saturday has a coefficient of 5, what does that mean about Saturday? If Saturday has a coefficient of 5, what does that mean about Saturday? It's what? So Darren has a coefficient of 2 right here. Darren is 2 years older than Brian. Emily has a coefficient of -3. Emily is 3 years younger than Brian. Saturday, not the fifth alphabetical. So wait, listen to this right. Good guess right there, Brad. Darren has a coefficient of 2. Darren is 2 years older than Brian. Friday has a coefficient of, Saturday has a coefficient of 5. So since Saturday has a coefficient of 5, Saturday is what to Friday? Because you have to go to the reference. So remember, Friday's the reference. Because Friday is the first alphabetical. So I'll repeat this again here and practice. Let's see if we can get in the chat. So don't worry, this is why I pause on this. Don't worry, Emily. 100 points, Emily, because don't worry, people are lightly confused. We'll figure it out. Kind of Sylvia. Sylvia's on the right track. But since it's 5, we know Friday is 5 whatter than Saturday. Look at the Darren, Brian, Emily example. Darren is 2 years older than Brian. Friday would be 5 units high. Oh my gosh. Saturday would be 5 units higher than Friday. Does that make sense? We'll see this in the equations in a moment. We'll be reviewing this a lot here. But Saturday is 5 more than Friday. Does that make sense? Saturday is 5 more than Friday. Or Friday is 5 less than Saturday. We can do it that right. Corbin and Megan, 100 points right there. But do you see how we have to reference the other day? Like when I say Darren has a +2, Darren's +2 means Darren is 2 years older than Brian. Emily's -3 means Emily is 3 years younger than Brian. Saturday's 5 means Saturday is 5 units higher than Friday. Do you see how we have to go to the reference? Saturday having a coefficient of 5. Here, I'll write it right here. We don't even need to know what Friday is. Oh, I think we have some good stuff in the chat. Here's Friday. And if Saturday has a coefficient of +5 and Monday has a coefficient of -1, then what we have right here is Saturday is going to be expected to be 5 units higher than Friday. Monday is expected to be 1 unit lower than Friday. Does it make sense when I draw it out right here? Does it make sense to see that Saturday is expected to be 5 units higher than Friday and Monday is expected to be 1 unit lower than Friday? I figure I should always draw things out. Like even me, like if I'm saying it, I'm getting a little bit confused. I'm confusing everyone. So Don't worry. Once again, if you say a wrong answer, it's just you thinking through it. We all make mistakes, and even I do. Um, and so remember, it'll be how the coefficient works right here. So this is how it works, and we'll see this in the model, and we'll see really strong interpretation here in a moment. Here we go. How many indicator variables will there be? If you have 7 days of the week, how many indicator variables are there? If you have 7 days of the week, how many indicator variables are there? Here's a hint. So I could ask this on the, yep, that's it right there. Because how many references levels are there? There's always how many reference levels? Hint. There's the answer. There's always one reference level. So there's always one reference level, and then everything else is an indicator. So you'll see some models where we don't have every day of the week. It's because we only used like 4 of them. If you have 4 days of the week, then you'll have 3 indicators. One of them will be the reference, whichever is first alphabetical, and then you'll have 3 indicators. If you have 4 seasons of the year, 3 of them are indicators. If there's 3 people in my family, 2 of them are indicators. And you can see this in our example where Darren and Emily were indicators and Brian was the reference. You only need one reference, and then you can compare everything to the reference. The key here is you always have one reference. You see it right here, and then the others become indicators. So here's with multiple, and the way it works is kind of like lights in a house, because when we talk about indicators, indicators only take on the value of 1 or 0. It is either spring or it is not spring. It is either summer or it is not summer. It is either winter or it is not winter. And if it's not spring, not summer, not winter, 1,000 points, it's what? If it's not spring, not summer, not winter, it's what? As in, it's none of those indicators. It's fall. Great job, Corbin, right there. It is fall. And that's when all the indicators are equal to 0. It's the reference level. So why do we not see female in this model? Why do we not see gender female? Why is gender female not there? Really good written test question. Why is gender female not in this model? Why is gender female not in this model? Because gender male. Female is the reference, bingo. Female comes first alphabetical, it's the reference level. So when we look at this right here, what does this difference mean right here? So it's in the notes, but I'll interpret it to you. 2 individuals who are otherwise identical. This is a what type of regression? Why is Brian saying otherwise identical? This is, I have to say 2 individuals who are otherwise identical. This is a what regression? I have to say otherwise identical. 2 individuals who are otherwise multiple. Once you see a multiple, you got to say otherwise identical. 2 individuals who are otherwise identical, where one is male and the other is female. The expected difference between their monthly salary is $458, where the male is expected to make more. And this difference is very statistically significant. When I say otherwise identical, I'm saying that they have the same education, experience, months, and then of course the interaction would do the same thing. But think about that. 2 individuals who are otherwise identical, where their only key difference is that one is male and one is female, the expected difference between their salaries is $458, which is actually the most significant thing in the model. It's the thing that difference there is the least likely difference by random chance. And that's controlling for the other variation. So do you think there was a decent lawsuit against the Harris Bank Company back in the 80s? This is like, yeah, that was a pretty decent lawsuit. If you controlled for these other variables, and you're like, after controlling for that other variation, we see here that there is a statistically significant difference between 2 people where one is male and the other is female. We expect the male to be making $458 more a month. And this is in $1980, which is like $1 million now. I'm just kidding. It's not $1 million. It's like 800 maybe. I don't know. What if we can ask Google? In 1980, how much would $458 be worth today?
I found this on the web.
Oh, it did 450. Here we go. Who thinks? Who knows what it is? It would be worth $1,500. $1,500. You're really close, Alex. It says $1,500 on here from 1980 to today. 3 times. I mean, I guess I'm getting old. That's pretty much near when I was born, so it's worth like 3 times the amount of money. I know, right, Brad? But Brad, you and I remember, like, I mean, quarters for a Coke was like a big thing. And then our parents would talk about like nickels for a Coke. I mean, my parents would be like, yeah, Coke costs like a nickel growing up or like 10 cents. And we're like, man, it costs a quarter now. And now you go to like a machine, it's like 75 cents or a dollar. You're like, oh, a whole dollar for a Coca-Cola? Ugh, ugh. Things are, I don't know. I went to the grocery store and I spent like $80. And my brother was like, I only got like 5 bags of groceries. I remember growing up when my mom would spend $100 on groceries and I was like, whoa. But she was feeding like a whole family of 5. Um, so it costs that much to make. Yeah, they've probably like with production and everything got it like really really cheap. And with like transportation, production, all that stuff, we've done really well on reducing costs. So I don't know, Coke and Coca-Cola, man. Which you should go back in time and buy stock in Coca-Cola in the 1980s. You'd be ridiculously rich. So or the 50s. There's an interest podcast about how Coke didn't change their price from 5 cents for like 50 years. Whoa, Brad, we should look into that. $100 for 5 people. Wow. Wait, what was that? I don't know. Okay. So the reference level right here, all this info on it. The level that comes first alphabetical is called the reference level. We should have that down instantaneously. How do you know what the reference level is? It's going to be the first one alphabetical, boom, and that's what we're going to compare everything to. Each other level is represented by an indicator. So if you have more levels, you represent them by indicators, but the first one's always the reference. The reference level has all indicators equal to 0. So when we talk about other models here, which we can look at some real quick, if we go to a model like this, where's Friday? Where's Friday? What the heck's going on here? Where's Friday? You might say where's Monday, Tuesday, Wednesday, but those were just not included. I'm just going to flip over my phone right here. Monday, Tuesday, Wednesday are not included. And so where's Friday, though? It's a reference level. It's not there. So what is the coefficient for Friday? Who knows what the coefficient for Friday is kind of technically? Because if we were to go back to get to Brian's model over here, if you look at the age thing going on, what would be like the coefficient for Brian's age? What would be Brian's coefficient if Brian had a coefficient? If Brian had a coefficient, Brian's coefficient would basically be what? It wouldn't be 38. It'd be 0. Because Brian's not different from Brian. So Brian doesn't have a coefficient. It's kind of like Brian's the intercept, because what's interesting, and what's really interesting about this, is that when you solve out these equations, think about what you're going to do right here. What are the only values you can put in for these? These right here can only take on the values of what? These can only take on the values like weekday Saturday, weekday Sunday, weekday Thursday can only take on the what values? 1 or 0. And if you were to plug in a 1 right here, what would be the new model? If you get this, you are understanding this lecture at like 1,000%. Who can write out the regression equation for a Saturday? Who can write out the regression equation for a Saturday? Go ahead and just round to like 2 decimals, write out the regression equation for Saturday. So what are you going to do? You're going to plug in a 1 for Saturday, and then you're going to solve the equation. This would be a very good test question. This is a great one. Yeah, good job, Alex, right there. Write the regression equation for Saturday. Write the regression equation for Saturday. I can check it by looking at it because I can see what's going to happen. And the reason I really like it is because of this right here. Write out the full thing. You need to write out the full, and I think it's on the next slide too. What's going to happen when Saturday becomes 1? Then start plugging in and start solving out the regression equation for Saturday. So Bill is just going to be times by this. It's going to be intercept plus Bill times this plus party size times this. Saturday becomes 1 times this. Weekday, Sunday. Grant close, but remember you need to carry your other coefficients. You need to have everything in the model. And it might just show it here. This is a 2,000 point question. If you get this, you really know what's going on. And it might just show it. But I want you to be thinking about this. I want you to try writing it down. So what's going to happen here? And let me do this. I'm going to show you how to do it, and I'm going to work it by hand right here, because I think it's going to help everybody. Okay, let's show how to do this from start to finish. When you're writing out regression equations, you need to start by just writing everything down. Let's do that right here. So we're going to close out the multiple, so I can just switch between. Did not close that? Nope. Okay, wait, good. Okay, so pretty close, Philip. Philip is very close. Philip, that's 1,000 points right there. Philip, you're very close. So we are predicting tip percentage, I think. So tip, Mila even closer. Mila very, very close. That's why. Tip percentage equals, and so we're going to write the full equation to start, and you'll see how it's easy with this right here. So we're going to write tip percentage equals, because that's, how do I know that? It's the y variable. So that's what we're predicting. This is y tilde x, 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 all the x's right there. And then we have the intercept, and the intercept is 20.56, I think, or 59. Yeah, it rounds to 59. And then we go right here, and we go plus Bill. Peel might be giving some great answers. I see some good stuff in the chat. Is it a negative coefficient on Bill? It's negative. Negative 0.27 times Bill. And then we go, does everyone know? So I'm just going to go here, 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 here. Does everyone see what I'm doing with this pattern of going through and getting the coefficient of Bill party size? So this is going to be 0.50 times party size. And I'm just putting this in like this. Does everyone understand what I'm doing with this part of it? And then we go negative 1.0 Saturday. And then we go here plus, and you can do weekday Saturday, I'm just abbreviating, 0.47 Sunday. And then we have minus 0.90 Thursday. Okay. We have now written the regression equation. This is the full regression equation. All I did was do intercept plus Bill times coefficient plus party size times coefficient. And it's a minus. Copy paste in the chat. Of course, you got it. Thank you, Alex, right there. There you go. Copy paste in the chat. So tip percentage, which we're predicting. So you could say predicted tip percentage. I mean, if you know regression, it's like, okay, we're predicting that. It's not saying it will be this. It's a prediction from the regression equation. Equals to the intercept plus the coefficient of Bill, which was negative, times Bill, plus the coefficient of party size, times party size, plus the coefficient of the indicator variable Saturday, plus the times Saturday, plus the coefficient of the indicator for Sunday times Sunday, plus the coefficient of the indicator for Thursday times Thursday. So if you look, I just algorithmically went through and went intercept plus this times this plus this times this plus this times this plus this times this plus this times this. Does everyone understand the pattern I did? When I realized that, I was like, oh, that's how you write it out. You just do this equals this plus this times 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 this. Once I saw that, I was like, oh, you just kind of just go through it step by step and just multiply each thing out and add them together. So it was literally like an epiphany. I hope someone's having that epiphany right now. And it's like, whoa. It's just, you just add them together and times them by what they're next to. Party size, whoa, dude. Party size will be just times by this, and you just add it to Bill. That's all it is right here. It's just right there, and it's been added together. Philip. Philip knows the trick. Because now to solve out the line for Saturday, Philip, you earned the 2,000. Philip earned it. Because to solve for Saturday, we do this. And then we reduce the equation to solve for Saturday. So who else wants to get the final 2,000 and solve out the equation now for Saturday? Who wants to solve? And I can do it pretty quickly right here. Who wants to solve? That's not the answer. That's the answer for Friday. Who wants to solve for Saturday? Mila, we'll give it to Mila. And so throw the last thing on there, Mila. Mila, you're basically right. Mila's basically right. You're just missing one thing. Just change the one thing. Mila, you got though. Not that part. Do you see the last thing right here? That right there. Well, great job. No, that's it. This is let's put up. Does that make sense right there? How about the equation for Friday? What would the equation for Friday have for all the indicators? Oh, blocking it. What would the equation for Friday have for all the indicators? If it's Friday, what would every indicator be? If it's Friday, what would every indicator be? If it was Friday, every indicator would be 0. And then we have to reduce. Remember to reduce it. So literally, if you solve this right here, This is a Friday question. Is this making sense right here, how the indicators only take on 1 or 0 if they are that level? You can't do some craziness like this. You can't have multiple indicators on, because this would be some day where it was a Saturday, Sunday, and Thursday. Indicators can only take on 1 or 0, and if every indicator is 0 like we see here, then it is Friday, because it's not Saturday, not Sunday, not Thursday, and our model was doing Friday, Saturday, Sunday, Thursday. So if you look at the data, because you don't have to have every day of the week, you'd only have indicators for the days of the week you have. Does this make a lot more sense right now? That this is a line right here for Saturday, and this is the line here for Friday. What is the only difference between these lines? What is the only difference between the two lines? Well, now it's really hard to see. The only difference between the lines is the what? I keep highlighting it over and over again. The only difference between the lines is the what? The intercept. In indicator regression, your lines will just move like this. In indicator regression, how will we know what the reference level is? If you have data like this and you want to know what the reference level is, like let's take this model right here. If you were to take this model, which we can just plug into R, we'll open up some R right here. Great questions today, everybody. Like a lot of, like, this is what it is when you're working through these things and you're like, okay, how do I do this? I got to save this one for today. So we need to do library reg class, because it's in the reg class. We'll load up tips. So once again, we get this output right here. And what you can do, because you can't really tell what it is, you want to go to summary, tips, $, and there you go. This is how you would know. I guess it does do it alphabetical. I don't know, I guess it does report them alphabetically. So when it runs this, it figures this out here. And there might be a way to trick it. I'm going to try something crazy right here that I've thought of. Let's say I want Saturday to be the reference level. There might be a way to trick it. Let me try this. Levels. And let's go to levels. I'm going to try something crazy here. I've always weekday, store into it the vector, and we're going to call Saturday 0 Saturday, just to see if we can get Saturday to be the first. So we're overwriting the levels vector, and I'm going to see if it does it, because I'm wondering if it will. So now I'm overwriting, I'm going to try to make Saturday first, or you call it a Saturday. Let's say someone were to say that. They said a Saturday. So now we've overwritten that. And now if we go to this, we see a Saturday. I don't think it's going to do it, because we have to reorder it literally. And then, yeah, you'd probably have to go to order. So there might be the way. Let me try one last thing right here. And yeah, you could report it like, this will just change the way it's reported. Dr. Petrie and I are looking into this one semester, but don't worry about that. That's just like, I was like, let's try to change it and let's force it to do this. And we figured out a way to do it. And I can't remember that way off the top of my head, but it's because of the way the data was originally coded. And you know what? This might change it. It's out of order though now. Because that, we'll do that. And now that's the order we want. And we've overwritten it. So now, yep, that did it. We changed the order. So if you're wondering what's going on, it's because the way R reports stuff is it alphabetizes them just by default, but then we didn't re-alphabetize them when we changed a Saturday. So if you're wondering what happened when I changed, it alphabetizes them by default, which makes Friday the first, but then when I renamed Saturday, it didn't re-alphabetize them. So then I went and re-alphabetized them so that a Saturday was first by overwriting the order. So I changed the order right here. And so technically this would all go through this order right here. So now if I run all this code in order right here, it should, yeah. So you can force something to be the reference level. So now every day is in reference to, I think I just renamed, trying to think through it. Yeah. So we technically could make a function that would generate the regression equation for a selected variable. Yeah, you could technically make it so that a selected variable would be the variable you're interested in. So you can do that. And I'm wondering, I did make it so the names changed, but I think I might have done something else. So don't worry. This is a bit of a crazy example, but I'm always like trying to break code and try to do things, but you can make it. So looking at the summary, we can infer that the tip percentage goes down by 1 on Saturday, up by, be careful. And we went right back to, let's go back to those notes we were just taking on here. So the way that this would be interpreted, Brad, really good question, is 2 days that are otherwise identical, where one day is a Saturday and one day is a Friday. The day that is a Saturday would be expected to have tips that are what lower on average. 2 days where one day is a Saturday and the other day is a Friday. The day that is a Saturday would be expected to have tips that are what lower on average. How much? What would we expect? 1%. And since it's and Brad is correct, since this is tip percentage, it would be 1%. Now that won't be for everything, because in our equation with gender, we have 2 people who are otherwise identical, where one is male. 2 people who are otherwise identical, where one is male and the other is female. The person who is a male is expected to make $458 more monthly on average. So remember, it's only percent for tip percentage because the units of Y is a percent. And I think about all these trick questions I can ask, because I can say like 458% more. No. This is in terms of salary. We're predicting monthly salary. So the 458 here represents 2 individuals who are otherwise identical, where one is male and the other is female. We'd expect the individual who is male to make $458 more than the female in their monthly salary on average. Does this make sense to everybody right here? Like what we're talking about? We're just interpreting the coefficient of an indicator variable in a regression. And we'll see this throughout the notes. So the coefficient's right here. No interaction yet, though. Interactions, we'll start interactions again by the end of today. We'll look at interactions again. So when we look at this right here, we have our classic interpretation. Once again, who are otherwise identical is what we must always say in a multiple regression. With these individuals, are we comparing otherwise identical 2 things at a time, the reference in the one indicator, or do we compare all of them? It's always one indicator to the reference. So when you look at this right here, it's always one indicator to the reference, as in we would look at Saturday, and Saturday would be compared to what day? Saturday is compared to what day? What day is Saturday compared to? Like Saturday's coefficient is 2 days that are otherwise identical, where one day is a Saturday and the other day is a Friday. We'd expect the tips on Saturday to be 1% less. What is Sunday compared to? What is Sunday compared to? You can keep answering the same thing. Sunday is compared to Friday. 2 days that are otherwise identical, but one day is a Sunday and the other day is a Friday. We would expect the Sunday to be 0.47 higher than the Friday in tip percentage. What is Thursday compared to? 2 days that are otherwise identical, where one day is a Thursday and the other day is a Friday. We'd expect the tip percentage on the Thursday to be 0.9 less in percentage than the Friday. What day do we see the best tip percentages? What day do we see the best tip percentages? From this data right here, what day do we see the best tip percentages? What day do we see the best tip percentages? Sunday. Sunday has the highest positive coefficient. What day do we see the second best tip percentages? What day do we see the second best tip percentages? This is a good test question now. What day do we? Friday. Because Friday doesn't have a coefficient. Friday is 0. Like, this is negative, and so this is why it's a good test question, because you have to realize that Friday's in here, but Friday doesn't have a coefficient. Does that make sense? Because that's where the tricky part comes in. It's like Friday has a coefficient of 0 because it doesn't change. Friday is the reference to everything. Thursday is lower than Friday. Saturday is lower than Friday. Saturday is the lowest. And I think we have a visualization of this. Here we go. Here's the visualization of it. Let me zoom in on it a little bit. So if you see here, Friday is the black line. The black line is always the reference level. And where is Sunday? Sunday is higher than Friday at all points. Where is, and that's Sunday, right? Yep. And then where are Saturday and Thursday? They're down here. Do you remember what the coefficients were for Saturday and Thursday? They were like negative 0.9 and 1, negative 1, negative 0.9 and negative 1, as though 2 days that are otherwise identical, where one day is a Friday and one day is a Saturday, we'd expect it to be like negative 1 less. And look, it's like a difference of 1%. This right here, this difference is that 1% difference. If you look over at the scale, like 2 days that have the same bill amount, where we have the same bill amount, but one day was on a Friday and the other day was on a Saturday, we'd expect them to differ by 1%. Does that make sense to see this here, like visually? Like, oh, if they're otherwise identical, well, we'd expect the Saturday to be 1% lower than the Friday. So yeah, it's just the visual right there. So hopefully seeing things like this kind of cement down like, oh, that's why we say 2 days that are otherwise identical, where one day is a Friday and the other day is a Saturday, we'd expect the day that is a Saturday to be 1% lower than the Friday. That's what we would expect. Not saying it will be, it's just what we expect. So one too many out. And we see the same thing going on right here, where we have two individuals who are otherwise identical. So they have the same amount of their education, I believe, in this one. And the reason you might say, well, why aren't we doing all the variables? The visualization doesn't work, sorry. So we have two individuals who are otherwise identical, where one individual is male, and so here's the male line, and the other individual is female. This right here is the literal coefficient. Does everyone see this difference right here is the differences between their whats? This would be their difference between their whats of the lines. Here's a hint. The hint's right here. This difference right here, which actually is constant throughout the model, it's the difference in their salaries, but it could be seen as the difference in their whats of the two lines. The intercepts. Yep. And it's because look, it's at all points constant. So we see here that you could take two, we don't have any data right here, but if we had a female right here, and if we had a male right here, then we would expect the difference to be that. This is the literal coefficient you are seeing, to where we would just add this amount. Like if somebody is male, we'd expect their salary to be that much higher than the female on average. So, and there might be, you might say, well, there's a little bit of nonlinearity. I don't know. There's a lot to investigate. It's always data. We always trying to look through it, figure out what's going on. And we got all the coefficients. Once again, we're doing lots of interpretations. And let's go back to, here we are with our interpretations. This is very specific. This is a key slide. So when we look at this right here, this is what I've been interpreting constantly. So the coefficient we see, that's the coefficient of the indicator variable, is the difference in y, whatever we're predicting, between two otherwise identical individuals, where one has the indicator level and one has the reference level. So that's when you hear me say things like 2 days that are otherwise identical, where one day is a Saturday and the other day is a Friday. The day that is a Saturday is expected to be this much higher than the Friday. This may be more of an in-depth than necessary, but would the area between those two lines be the total difference in salary? It'll be the coefficient. So whatever that difference in the lines is this coefficient right here. So we can actually say that the difference between the two lines that you just saw, that 461, and you could kind of double check graphically speaking, that difference right here, because this is the graphic for it, is 461 at all points. So that difference right there is the coefficient of gender male. So this difference right here is exactly 461, because that's the coefficient of gender male. And we see that, we have that model right, where'd it go? Here it is right here. So we have education and gender male, and the coefficient of gender male is this, and that's that difference between the two lines. So think about this. When would this be the least significant? If it was 0, and then the lines would be on top of each other, and then it wouldn't matter. And then the p-value would be 1 because it would not be significant. So is this, hopefully these all making sense right here. But we see interpretations. These interpretations are key when you're doing your assignments, and you should be able to kind of say it without looking at it. Like two individuals who are otherwise identical, i.e. they have the same education, are expected to differ in their salary by $461 between a male and a female, where the male is expected to make more. And I think I'll redo that ending. Two individuals who are otherwise identical, i.e., they have the same education, where one is male and the other is female, are expected to differ by $461, where the person who is a male is expected to make more. And yeah, this is where you should practice it. You should understand what it means, and you should be able to interpret it. I keep teaching like I'm going to have you guys do the written test, and man, I'm just thinking about how to make these. I'm not trying to make the hardest test in the world, but this is where I see people make mistakes. And I write things on the test like males will make 461 more than females, or I leave out the are otherwise identical. So I'm already writing these test questions in my head right now, where I leave out things like are otherwise identical, or I say males will make more, and we've said how these things are tricks. So I'm thinking of the mistakes I see that people do on the written test, and I'm trying to translate these written mistakes into multiple choice mistakes. So that way I'll put the mistakes I see to make sure people aren't making those mistakes, as though if I had you write it out, you would not make that mistake. This is not what we will see as a difference. It's what we expect to see, and it's between two otherwise identical individuals. And we could compare this right here. You can compare two separate levels. So when we go back, if we were to compare Darren and Emily right here, what is the difference between Darren and Emily? If you were to compare Darren and Emily, what is the expected difference between Darren and Emily? What is the expected difference between Darren and Emily? 5. Yeah, it's just how you do it. What is the expected difference between, if these are tip percentages for Saturday and Monday, then what is the expected difference between Saturday and Monday, and which day is expected to be higher? If these were the coefficients of tip percentage, like predicting tip percentage, then you would expect Saturday to be this much higher than Monday in tip percentage. If you were to compare Saturday to Monday, you'd expect Saturday to be this much higher than Monday. 6. That's it. That's how you can compare two indicators, is you just take the absolute value of their difference, or you take the total value of their difference. So we kind of know how to do these things. A lot of statistics is things that we already know how to do, but we don't realize it applies to just doing mathematical models. If we're looking at this coefficient, the coefficient here is in reference to what? This plus 5 means that Saturday is expected to be what to what? This plus 5 means Saturday is expected to be what to what? So we see plus 5, we're like, oh, that means it should be what? Plus 5 to Friday, exactly. And then this is minus 1 to Friday. So when you think, okay, if this is 5 above Friday and this is 1 below Friday, well, that means that they have a difference of 6. It's just the same as when we talk about our siblings. If this person's 2 years older and this person's 3 years younger, then the difference right here is 5 between them. So you could even figure out Emily's 35, Darren's 40. So like, oh no, Darren's 40. Oh, he'll be 41 this year. Is that right? Oh no, that means I'm getting close to 40. No. Once Darren turns 50, I said when he turned 30, I was like, once Darren turns 30, that'll be so crazy. Now he's 40. Sorry, Darren. Like, why are you talking about Ryan? So we see right here, we have all of our coefficients. We could compare different days. And here's the coefficient of Saturday. So let's hop back to the main screen. Here's the coefficient of Saturday right here. And we see right here, once again, we've been interpreting this multiple times today. All else being equal, 2 days where one is a Saturday and one is a Friday, the expected difference between the 2 days is 1%, where the day that is the Saturday is expected to be 1% higher than the day that is the Friday, or 1% lower, excuse me. I saw the smaller at the last moment. And so now you could compare Saturday to Sunday. All you do is just take the absolute value. This is exactly what we were just talking about here, not the absolute value, excuse me. You just take their total difference they are apart. If you see this is basically 0.5 and this is -1, so you just take their total difference, like how far they are apart. It could go through 0, so don't just like be careful. But like if one is 3 and the other's -2, that's a difference of 5. They're 5 apart. Just think of it like a number line, like how far are they apart on the number line? And that's the expected difference between a Saturday and a Sunday. And we'd expect the Saturday to be higher. And now we get into our lines. We've been drawing this out. Okay, this will probably be, I think, our last part today. Let's do it. So the vertical offset right here, which is the difference between their intercepts, is what we're trying to measure with the indicator variables. The indicator variables will just change the intercepts. That's all it will do. When we have a higher coefficient, it'll be more significant. And we need to figure out if these are actually different. That's going to be a key thing right here that we'll be getting into. When a categorical variable does not have an interaction with it, all the lines will be parallel. And I want to mention something big for yesterday. Let me hop back to drawing on the screen right here. We kind of alluded to this, but I want to say it explicitly. The weaker an interaction is, the more parallel a line is. Now, this is what you were seeing earlier. These lines are parallel, which means there is no interaction at all. Does that make sense? The stronger the interaction, which we might still have our drawing up from yesterday, we do. The stronger the interaction, the more perpendicular the lines will be. Because look at this one right here. This was when we talked about toothpaste, bacon-flavored toothpaste. You see a very strong interaction, as though the way in which the adding of bacon to a product changes the taste is influenced by what product it's on. So we see here that bacon does not have the same effect. But take a look at what we just did. Here, if this is education at the bottom, so if that is education, and then this is male, and this is female, the impact of education, to go back to earlier stuff we talked about, is basically what throughout the model. The impact of education, C word, like a mathematical C word, but not in that term. It's basically what throughout the model, 1,000-point question, who knows, waking everyone up right here. The impact of education on males and females is basically what? The impact of education on males and females is basically what throughout this model? The impact of a constant, Ryan, 1,000 points earlier, right? It's constant. It's the same. That's what, there's no interaction. But if there was an interaction, which we could do very easily, to make an interaction term, all we do, we just load up the salary data set, and then we go here, and we make a model where we predict salary, tilde, gender, plus well, here's the original model. We'll just do this for the moment. Data equals salary. And there's the model. Visualize the model. And here's our model. We'll make it much bigger. There's the model. And you can see the constant impact because it's the same throughout. But to throw in an interaction, there you go. Now the lines are not parallel. We also get a p-value on the interaction. More on that soon. Which means we can say it, the interaction does not bring additional information not accounted for by the other variables in the model. And we also see that if we do a summary on this, that we do have, gender male is not significant. And I bet you, see, there you go. Lots of interesting stuff. Lots of ways. Is VIF? Could not find, it's VIF capital. Now, there is some collinearity. And that's really interesting. So the two things are overlapping. We see a drop in there. Let's look at, I am very interested in this. That's so interesting. I should show that to Dr. Petrie. It's so, what's so interesting? I want you to look at this. Look at how everything in this model is significant. Everything in this model is significant. The model itself is also significant. If you add the interaction, nothing in the model is significant. With the additional variable, nothing in the model is significant, and the model is a little less significant. The R-squared adjusted did go up, and the typical miss did go down. But with the extra interaction variable in the model, nothing is significant, even though the model is ridiculously significant. The model itself is ridiculously significant, and nothing in the model is significant. Statistics is awesome. That's just like, what? Meanwhile, without the interaction, and just so people are wondering why right here, and we do see some of it, but I thought it'd be even worse because we're seeing if you notice where the interaction is, there's some major collinearity. Well, I mean, it's not. 5 to 10 is generally considered high. Like if you literally look up what is high multicollinearity of VIF of 5 to 10. So this is in the kind of high range, but it's not ridiculous. We've seen, like when I do some examples, I purposely make it insane. But the literature would say multicollinearity between 5 to 10 is pretty high. So when we can say, when is variance inflation high? and they'll say between 5 to 10. And so there we go, a cutoff of 5, but then some people will say 10. Like if I Google search 10 right here, greater than 10, everyone says like 5 to 10. People will literally say 5 to 10, and I'm like, well, which one? I don't know. Oh, someone's saying 10 right there, but I thought we saw 5. There it is, cutoff of 5 right there. A cutoff of 5 is commonly used, and then someone else is like, in practice, a VAF greater than 10 is high multicollinearity. So what do we have right here? We have kind of high. I mean, that's very close to 10. That's bordering close to 10. But so if you can't tell, we are doing the same sorts of things again and 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 again. Does everyone see how important the multiple regression is? Because right now we're doing multiple regression. All we've changed right here is that this variable right here is what in this. This variable right here, either one of these, is what in this chapter. The x variable we are using now gets to be what? Who knows? 100 points right here, who knows? The x variables in these chapter get to be what? For the first time ever, an x variable in a regression can be what in this chapter? What's the whole point of this chapter? That all of these x's get to be silence. What is the difference? Categorical, Brad, you're right. Yep. All of these x's get to be categorical. Not all of them. I mean, we have education here, which is still quantitative. But this goes to, especially when I think about test questions, once again, is that there's a different interpretation here for education. It'd be 2 individuals who differ in their education by 1 year are expected to differ in their monthly salary by $53. So the person with the higher education is expected to have a higher salary. This one right here is 2 individuals who differ, or 2 individuals who are otherwise identical. Forgot that for the other one. 2 individuals who are otherwise identical, where one is male and the other is female, are expected to differ in their monthly salary by $461, where the male is expected to make more. And what was the coefficient down here? You see the coefficient went down, but then we have an interaction right here that if somebody, none of it's significant though, which is so crazy. And I could really do something here to figure out the best model. I might do this in 474 because I am interested. Do people want to see the best model for this? We have just enough time because we want to see what we should do. I'll show you what we should do to figure out. And it's all going to be math. And I'm not going to be able to control it. And we'll see what it tells us. What we need to do is we need to make a model and see if it works on new data. It is a glimpse into the future, especially if we're taking 474. So we talk about what is the right way to do it. Here's the right way right here, the data mining using Carrot. So what we're going to do, and this is just a quick aside because we've done a lot of notes today, and so this is my quick kind of bonus at the end of class, and we'll finish up the notes tomorrow with interactions and all this good stuff. We've been interpreting coefficients, so if you're wondering what's going on, we've already done a lot of interpretations on coefficients. Throughout all of today, we've been interpreting, and it shows the mathematics here that the expected difference between these two levels would just be differences between the two things what's-is. When we look at two indicators, the differences would only between their what's-is. Look at the B0 plus this, B0 plus this. The differences, mathematically, are just their differences between their what's though. So, but this is B0, and we're just adding something to B0. This is B0, we're adding something to B0. They'll only have different intercepts because that's the B0 we're changing. So when we change these models right here, we're just changing the intercepts of the lines. If there's no interaction, we're just changing the intercepts of the line. That's all we're doing mathematically. So if you look right here, let's do a quick practice. Make sure we have this before we do our last little bonus at the end. Who can write the implicit equation for gender female? Write the implicit equation for gender female. Give it a shot. Should be able to do it like that if you know how to do it. Write the implicit equation for gender female. Hint, that becomes 0. Write the implicit equation for gender female. Implicit equation means we're just going to solve it out, make it just look like a math equation. And so write the implicit equation for gender female. If you're following along and you know how to do it, that's awesome. You're right on track. Let's see what people say. What will gender male become? Gender male will become 0. And then we'll times 0 times something. I think we got it right here. Brad, that is right. Wait, Brad, you forgot a decimal. You got 53.8. 53.8. 53.8. So Brad is right, but he just forgot the 3. So does everyone see what Brad did right there? All Brad did was just plug in. And remember, we're predicting salary. So we're predicting salary. Salary is the Y variable. So make sure that salary, so this is good that we're practicing right here. No, don't worry, little small typos here and there. And look, everyone's just practicing. This is why I want you to be here and typing it out, because if you can do this and you get it down, you're like, okay. You have to be like, okay, what's the Y we're predicting? And then we have to go through this. And but careful. Remember, there's no gender female indicator. The indicator is gender male. So I think Ryan looks to have it. Ryan has it perfect right there. Ryan's answer in the chat is perfect. What is the regression equation for males? What is the regression equation for male? Who can solve out? Another 1,000 points. Ryan, you got 1,000 right there. Great job. What is the equation for males? What is the regression equation for males? And we would just solve it though. Since what it is this literally becomes a 0. So when it's gender female. And so that is, Philip has the equation for females. That is the female line equation. And what is the equation for males, though? What is the equation for males? And I think I basically know it. It'll be on the next slide, I think, so I can show it to you. But try practicing this. These are things we need to be able to do. What is the equation for males? And so what would this become? This would become a 1. And make sure to solve it, though, Nicholas. Make sure to solve the whole thing. So what, if it's males, then what will gender male become? Remember, gender male only takes on 2 values. Gender male can only become a 1 or a 0. So if somebody is a male, what will gender male become? And then we'll have to solve that. Brad's got it right there. Brad, another 1,000. Yes. If you're getting it right there, you're seeing what's going on, because you're just plugging in a 1 right here and then solving it, and this will change the what. What's the only thing that changed between their equations? The only thing that changed was the intercept. And we're just adding the coefficient of the indicator. That's what all this math right here on the screen, which looks like a lot, is just showing you that when you solve, you either put in a 1 or a 0, and it's only going to change the coefficient of the intercept, which is B0. So when you solve this out, you really just have a difference between the intercepts going on right here. And we see that as we solve through this, and you can see the math here on the screen. So it's good to just practice it though. Like, try to solve it for yourself and be like, can I solve this? You're just plugging in, and then you should reduce down. I wish the slide showed it here. Well, it does, kind of doesn't. It just shows that, and then we should reduce it down. Here it is reduced down, and we see every single line right here. So we've been practicing this. Like, throughout all of this, we've been practicing every single one of these. Let's see, attraction. So many things right here. You can do multiple indicators right here, where you could figure out if somebody has glasses or no glasses. This is how you know if something is an indicator, because it'll have the level glasses, no glasses. So glasses has the level glasses, and glasses, no glasses. And glasses comes first before no glasses. Fitness score. Why does fitness score not have why does fitness score not have fitness score yes or fitness score no? What? This is where people get confused. Wait a minute. Fitness score. What is the reference level for fitness score? What is, and look up here, it just says fitness score. What is the reference level for fitness score? Help me out with this. What is the reference level for fitness score? What is the reference level for fitness score? Help me out with this. Boom, Grant. Thank you, Grant. That's worth 1,000 points. That's what you should identify immediately. It doesn't apply to this. That's not what we're doing. Great job, Grant. That was a trick question. Nope, does not apply. Fitness score is quantitative, so it's 2 people who differ by their fitness score by 1 unit are expected to differ in their attractiveness rating, because we're doing score by 0.26, or the person who has the higher fitness score is expected to have a higher attractiveness rating. If you look here at glasses, glasses has the indicator no glasses and has the reference level glasses. So glasses goes down here and creates an indicator. So if you look at how this is added to the model, it creates an indicator. You don't see glasses here, you see glasses and the indicator no glasses, which is part of it. Parent race, we've got parent races right here, and those are the indicators. So, and then there's the data set right there. Pretty decent model and all this good stuff. I'm trying to think. Let's mention significance here. We don't have enough time. I don't want to do that. Let me say it. I'll just say it. Ooh, look at that. Look at that. And let me say it because it's on this slide. So how many things can we drop in and out of a model at one time? How many things can you take in and out of a model at one time just by themselves? That's the answer. How many things can you take in and out of a model at one time? How many things can you take in and out of a model at one time to just like be like, no, let's take that out of a model? One. So how many levels of decade are there? Ooh, this is a trick question. This is such a trick question on the test. Oh, be careful. How many levels of decade are there in the data frame? And the answer's on the top of the slide. This is when someone says there's a problem on the test. Be careful because I know it looks like that. There's 4. That makes it a little trickier. That's a combined level. So if you look right here, that's a combined level. They're putting 60s and 70s together into one level. And also here you would know there's 3 indicators and there's always one reference. So there's 3 indicators and there's always one reference. Does that make sense? 3 indicators, then there's 4 levels because there's one reference. So lots of good practice from today. So what do we have to do? I'm going to do it. I'm going to give someone 10,000 points. I don't care. We're going crazy. So I really want you to think about this. What do we have to do? And you have to give the right answer. If you're listening, start paying attention. I'm going to start giving wacky points here as the semester starts to end. What do we have to do to take all 3 of these things out of the model at one, just like to take all 3 of these things right here and just toss them all out of the model and look at the difference between the models? I want to take all 3 of these things out of the model at one time, just like that, and then compare 2 models. I'm going to take all 3 of these things and toss them all out of the model at one time. And then I'm going to compare the 2 models. So I'm going to take all 3 of these things right here, toss them out of the model, and I'm going to look at the model without those things and the model with those things and compare them. So I'm going to take all 3 of these things and make a model without it, look at that model, and then look at my model and see if the model works better with these 3 things. Henry, amazing job, well earned. I'm showing you the graphic. If you remember from the notes, you go from the simple to the complex, and right there, and Andrew's kind of hitting upon it too, because we're going to create a smaller model, which Henry, you're 100% right. Great job, Henry, well earned, and I really mean it. So make sure to send me those points. You are correct. That's a partial F, because we're going to drop these things out of the model, and we're going to look at the difference between the simpler model and the complex model. That was a very tough question because it was a big review question from earlier. And this is why I kept saying throughout multiple regression that and don't worry, it was meant to be tough. That's why I throw out crazy points for things like that, where it's like, okay, wait a minute. Brian's talking about, thank you everyone for giving Henry some props right there. Tough question. We are looking at, let's take all of these out of the model. We're just going to go drop them out of the model. And then we're going to look at a model with just 0 points. What? Well, you're doing great, man. And look right here. The partial F test is done right here. This, I know, crazy, man. You're like, I got this. So the partial F right here is done for us. So is the impact of decade statistically significant? The impact of decade is statistically significant. And when we look at, let me just say this. Right here, these p-values are trying to see if decade 2000 has a significant difference from what? Last question of the day. This p-value right here is asking, is decade 2000 significantly different from what? This p-value right here is asking, is decade 2000s different from what? You're right, Brad. And if you notice, it's the most significantly different because here's the 2000s decade and here's this. Do you see the 1980s decade? That is the least significantly different from the reference level. So we don't really care about the p-values of the indicators because the p-values of the indicators tell us if they're different from the reference level. We care about the overall effect of adding the variable. And to figure out the overall effect, we have to drop everything out of the model at once. So we'll look at this more tomorrow. Perfect end right here. I'm going to go over to the other notes. Okay, so we're going to figure out the right model here. Let's do this. Let's figure out what's really going on right here with this data. Okay, so we need to go here, where this is just fun after class stuff. And so we're going to make a training and a holdout. So 474, if you're here, this is training and holdout stuff. And we're going to see what's actually going on with this Harris Bank data. And we're going to make the best model we can. And we're going to see what a predictive model should look like here. So this is predictive modeling for 474, even though 474 hasn't started yet. And this is a peek into the future if you're in 320 right now. And you're like, well, what do we do in 474? How do we make this more advanced? So we're going to go right here and we're going to take a sample of our salary data. Now we're going to go 1 through the number of rows of salary. And we want to take, let's do 75%. So, and that gives us our train rows. And then we're going to go here to train, salary, train rows. And then we go here and we go to holdout and we go to here. We need to get a fit control. Let's go get a fit control out of here. And let's use repeated CV. Why not? I'll use CV. We don't want to go too crazy. And there's our fit control. And, oh, we don't have library caret on yet. Let's go to caret. And there we go. Library caret's on. And then we need to go and make a model. We're going to use elastic net regression right here. So let's go down to an elastic net. Regularized regression 2. Did I make that one? Regularized regression expand grid. Here we go. And there's the GLM net. And here's our code for it. So there's the GLM net. There's the code. And we can plot it. And we got the best tune, everything, results, how it works on new data, RMSE, coefficients in the model. Cool. I think we're good. Let's take all this code right here, and we basically have it. This is why this, there we go. So we need to go here. We need to change the Y to be salary. Is it capital S? I think it's that. And we have the train data. And we need the tune grid. Where's my tune grid at? I didn't take the tune grid. Oh, I didn't take the tuning grid. Yep. You have to know what you're missing, because if we don't have a tuning grid, we won't be able to do it. So there's our tuning grid. And now there's our model. Let's see what's going on with the model. Ooh, interesting. Let's make a finer tuning grid. So we're going to go here. Regularization parameter. That's going to be our lambda. So let's go to 0.1. Here's our best model down here. And let's look at it. Best tune is the alpha. It looks in there's the best model. GLM net, row names, post. Oh, one like that. Uh-oh. And we do get gender male in there, and this is the best model. Hey, Brian, when you get a chance, could you take a look at tomorrow night's homework 474? I'm not passing any of the standard checks, and I'm getting things. Ooh, we should take a look at that. We might do it after class. Yeah, it might be, send me what you're getting, Jordan. Send me it as soon as possible and be like, hey, Brian, it's not doing it. Oh, and these Y variables right here are not the right Y variables. That's why we're not getting the things right here. Send me that as quickly as you can, Jordan. I'll take a look. Here's the easiest thing to do, Jordan. And I might have to send out an email. Try one of these. Try one of those. That might be the issue right there. And we were doing this problem right here. So let's take a look. So this model right here explains 45% of the variation. It typically misses monthly SAR by $384. And is this on the holdout? Whoa. Wow, it does even better. Whoa. This model does way better on the holdout. So the answer is the best predictive model we have actually has a coefficient of gender male. Do indicators in the reference both count as levels? Yep. There's always one reference, and then there's as many indicators as remaining levels. So there's only one indicator here because we have male, female. So there's only one indicator for gender male. And if you notice, I just went through, for those watching, it did. That's what I thought, Jordan. I need to send out an email about that, because believe these things have driven us mad in the past. Sorry, Jordan. In your email, be like, hey, Brian, send out a quick email saying, hey, change it to sample kind equals rounding. It's just the way it generates the random numbers. No, really good question right there. Yeah, there's so many things to juggle. And I really like that in 320 today, we brought this to doing predictive modeling. And what's so crazy is, if you notice the structure of this code, I didn't really have to change it. I know what this code does. We recovered this a lot in 474 lately, like what every little bit of this code does, which hopefully 474 understands every step of this. Jordan, would you say you understand everything, every argument in this code? Like, do you understand every single argument I have on a new line? Would you say you do? 320 probably is like, no way. How do you do that? Hopefully you understand every argument in that code right there. Yeah. We just have to know what each part means and theoretically what we're doing. And it seems super complicated. Like, especially if you were to start on 320, I'm like, I'm going to tell you what every bit of this code means. You'd be like, what? It's just like, I go, here's the formula. We're going to predict y from all the x's. Here's the data set it's in. Here's the method we're using, which is elastic net regression, lasso ridge being combined together. You also see that right here with the tuning parameters we're using for it. And then here is the fit control, which is the k-fold cross-validation chosen right here. That's where this line of code connects to kind of this right here. And the pre-proc center scale turns everything into what? We'll take a quick break. 1,000 points, start class. We're not started class yet, but this turns everything into what's? Say it with me. Turns everything into, we know what it turns it into. Who's got it right here? 1,000 points. Who knows? Turns everything into z-scores. Sarah, great job. I need to make some 474 graphics. I keep thinking about that. Like, I really need some 474 graphics where it says like BAS 474. Like, I don't know. We need a general purpose one. But good morning. How's everyone doing? We got the Red Bull today. We're doing great. I do want to say this. Man, my brain overheated yesterday, but who stayed after class yesterday? And we showed that everything we were talking about, we showed it with the graphics. We computed it. We showed how to draw everything perfect. So, guess what day today is? It's my anniversary. Is that? What day is it? Yeah, out of state after. It's Taco Day. I like Taco Day, but we got it, we proved it, we showed we have it drawn correctly. We went through. So sorry, my brain overheated yesterday. What day is today? You got me wondering now. But we went through, we did everything, we graphed it out, and we did each and every drawing for the AUC bingo night. We did each and every drawing for the AUC ROC. And so if you're wondering, just go to the last, like, I'll try to make it like when I put the timestamps in later tonight, probably, I'll try to put like a thing like class and then like AUC ROC properly explained. Oh, thank you, Nin. Thank you so much. So, yeah, I think here. So it's 98 months. 98. I'm totally, I don't know. She'll be like, I don't know. She'll probably like at 100 months, she'll stop. I'm like, I don't know. It's just so much fun. Thank you so much for the happy anniversaries. So I'm excited because in like a week and a half, I'll be able to see my fiance, and it's really exciting. So very exciting times. And one thing I also want to mention is I ended class for 320 today by going into predictive modeling. And if you notice, there really is a big jump between these models. And so who knows to start, Jordan, thank you very much. For 1,000 points right here, there's a big jump between going through these models. And this right here indicates that there's a big difference between these models and this model. And I know we could look at the notes and figure out which model this is exactly, because I always forget. So I should go look at the notes and cheat and be like, I know it's one of the two, but what is this controlling right here? What is the mixing percentage controlling in regularized regression? What is the mixing percentage control in regularized regression? Thank you, Hannah. What does the mixing percentage control in regularized regression? Lasso and Ridge, exactly. 1,000 points right there. Jordan, crazy points today. You can get up to 1,000. So I just gave all the points right there, Jordan. So he's got all the points. Everyone gets points from Jordan now. So it's controlling the mixing of Lasso and Ridge right there. And it's one of the two. I mean, when we interpret it, we could say like, yeah, it turned out to be all this. But the mixing percentage right here is how much Lasso and how much Ridge we're mixing together. The regularization is the penalty we're putting onto it. So we're doing a different amount of penalty based on it. So, nope. And we can see here just the different amounts we're doing throughout the model. And yeah, so pretty interesting what we have going on right here. And we see the different amounts, all that good stuff right here. And yeah, this was a model we made to predict the salary of individuals. And what we saw something pretty interesting in 201. We saw in 320, excuse me. We saw this really weird thing today where when we were predicting people's salary, when we used gender and education, the model was very significant. And we saw significant coefficients on gender explaining somebody's salary. So as everyone see here, gender in this model is actually the most significant thing. But when we add in the interaction, here's what happened that was so weird. We saw that now, what is significant in this model? Now, the intercept, no one cares about the intercept. What is significant in this model right here? What variables are significant in this model? What variables are significant in this model? What variables are significant in this model? And, well, it is true that the intercept is statistically significant, but the intercept's like, meh. None. Nothing here is statistically significant. That's not. So we went from a model where both things in the model were extremely significant. This is super significant. This is this is ridiculously significant. This is very significant. And now, this is definitely not. I mean, this is basically not. It's so close to 0.05, but still it doesn't meet the 0.05 standard. And this is not. Our model itself is statistically significant, but that's not how we do things in predictive analytics. What I did then was I made my training rows, and we're going to get a different result this time now. And I made my train and my holdout. And then I went through, I made my fit control, which controls the what portion of the data. This is key, this is review. What kind of data does this control for 100 points right here? What portion of the data does this control right here? The fit control controls the what portion of the data when we're making our model. There's 3 portions of our data, and one is kind of inside of another. The fit control controls the what portion of the data. There's 3 portions. Here's a hint. One of the portion is the training. Closer. One of the portions is the training. The fit control controls how we, so I guess it does kind of control the training, but the fit control controls the what portion of the data. And the hint is right there. The fit control controls the what portion of the data. The fit controls how the validation. The fit control controls the validation portion because it's the k-fold cross validation, or at least that's the one we're using. Jordan and I were looking at a lot of this yesterday. We were looking at all the different things. If you stay tuned until way after the video, I was like going through and I was doing like text searching and fun stuff like that. So this controls the validation. So this controls the internal validation of the model, which is how we will pick the model. We pick our model based on the validation. So we pick our model based on the validation, and then the tuning grid right here, this is the tuning grid. The GLM net grid is a tuning grid. You could call it tune grid. Like you could go here and call this tune grid. Like it's just the default name from the output. And so you could go here that the tune grid equals capital tune grid. Just make sure whatever you call it, it's in the same spot. So you don't have to call it something. You can just call it whatever you want. And we are using a different data set, so we'll see a different result than we saw last time. And this is how we're turning our knobs and dials. Does this make sense here that the tune grid is like, okay, I'm going to let alpha go from these values to these values. So if you look here at the values of alpha, you have values of alpha going, and we should see, here's the values of alpha right here going from 0 to 1 in increments of 0.25. Let's take a look at the code. Alpha will go from a sequence of 0 to 1 in increments of will it show it? From 0 to 1 in increments of 0.25, exactly what you see. Regularization, we usually do it on a scale, the lambda, which is the penalty down here at the bottom. We usually make it like it can be very small values. So if you do this right here, you can see lambda is all of these numbers here. All of those are all these little dots. Does that make sense that all of these values here are the dots across here? Like you should, whenever you see a graphic, like the graphic behind me, boop, you should understand what's going on right here. That each of these lines is represented by the alpha, and each of these dots going across is represented by the lambda. So we have all the different values of alpha. Let's highlight this and show this. So all these different alphas are like, this is an alpha of 0, and then we do all the values of lambda across it. So as we're seeing all the values of lambda across here, which is the regularization parameter, which is the penalty we're adding for the weight of the coefficients. And then you go to the next line, which is this one right here, and you go across it right here, and you keep doing the different lines, and they can do kind of different and interesting things. But this is how much we're mixing our lasso and our ridge, and this is how much we're penalizing ourselves down here. So actually, it's truthful that we want a very small penalty. And so, yeah, that's what this graphic is doing. And what's interesting is when we make this, we go down here to the best result, and there's the best result, and then we get the data from it. The typical miss the model makes when it predicts somebody's monthly salary is about $332. And then we see right here that on the holdout, this one actually did worse on the holdout. The previous one did better on the holdout. This one does about 383 on the holdout. It was estimated to do this. So what is Brian doing? Brian is seeing if his model is what right now? Brian is going to see if his model is what? 100 points in the chat. Brian is checking to see if his model is what? Brian is seeing if his model is what right now? By looking at the ratio of how it does on the holdout to how it did on the validation, Brian is checking to see if his model is what? By looking at the ratio of how it does on the holdout to how it does on the validation, Brian is seeing if his model is what? Brian's saying, okay, here's how it works on new data. Here's how I thought it would work on new data. Not necessarily seeing Carly, 100 points right there, good guess. So I'm looking at how well it did on new data. This is how well it did on new data. This is how well we thought it would do on new data. And I want to see what the ratio is. No, I don't like that. Nitin, you're on the right track. 100 points in right there. Overfit. Yeah, Yao Ji, totally right. We're seeing generalization. Yeah, we're seeing how, because this is how it generalizes to new data. This is how we expected it to generalize. You want to see if it's overfit. Phaedron right there, 100 points. Yep, and Sarah. So we want to see if it's overfit. That's what I'm doing right here. I'm checking to see if my model's overfit by looking at the ratio. You could literally code this in yourself. Like if you think about things, so you could take, let's go. Okay, so this is on the thing right here. So let's call this holdout test. And so from the holdout test, good, there's the RMSE. We'll do as.numeric, or we could do unname. There's a function unname, all the functions you have to learn. It just takes and does that. And then we want the best results right here, and we want the RMSE, which is 1, 2, 3 again. So let's go to val test. And so the val test and should just be the same thing. So let's take this. I think, okay, then it'll be the third position in the val test. And so that should be the RMSE right there. Yeah. Does everyone see how I found the RMSE? Does this make sense, what I found right here? I took and stored this in, and I have this right here, and now I can get that same ratio. It's treating it as a data frame. We don't want that. I thought that 31 might be a problem. There we go. That value right there that we see of that, this value right here, is all I was trying to obtain with right here. Does that make sense? It was this val test previously, this problem right here, this was being treated as this. It was being treated as a data frame, and then it got mad here and it said this data frame stuff, so I turned it into a numeric. So instead of it looking like that, it looked like this, and that's just a vector with one thing. So I had to turn it into as numeric. So there's all these little things you have to do because it was treating that as a data frame. Does everyone see the small difference right here? That this object right here was a data frame. It was a row in a data frame because it did some data frame calculations on it and it didn't like that. Do we always want a small RMSE, or does it depend? You always do. Smaller RMSE is better, but what is small depends on the problem. So when you're like, what is a small RMSE? That depends on the problem. So does that make sense, Sarah? It's like, well, what is small? If this is somebody's monthly salary, it's kind of small, especially in $20 that's kind of small. If that's yearly salary, that's a very small miss. Like if I can predict someone's yearly salary and typically be off by about $332, like when I predict someone's yearly salary, I typically miss their yearly salary by about $332. It doesn't mean I will miss it by that. It just means I'm off by about that amount on average. Now that'd be really great for yearly salary. For monthly salary, it's pretty good. If it was weekly salary, that'd be like, ooh, $332 is how much you're typically off when you predict someone's weekly salary. So the big thing is context here, Sarah. It's like, well, what does this mean? And that's why we're always practicing interpreting. And we don't want to look at this as just some random value we calculate, like, hey, 332. It's like, okay, what does that mean? And the big thing we're going to do right here, thank you, Sarah. 100 points, Sarah. Great question. Let's just take and let's call this overfit test. So what you can do here, overfit test, you can say if overfit test greater than or equal to 0.10, and then we could just say cat, your model is overfit, else, and then you go here and you say cat, your model is not overfit. And then we could put not like capital. And so when we run this now, we should just get to the screen. Error. Where's my error? Who can help me with this error? Your model is overfit. Error unexpected blank and blank. Unexpected. Where are we getting the error? Somebody help me out this. So if this, run this. Oh my gosh. What am I doing? There we go. I just forgot the parentheses on the cat. So with this right here, you can see this will actually do it for us. So you could actually program all of this in here for you to run this out for you and print this output so you could test to see if models are overfit. So this could just compute the value of the overfitting and then do it for you. So we could do this with different random samples, which would be pretty nice. So I'm just going to run the same results right here, splitting it up and rerunning this, and we'll just see if we get that model was overfit. I wonder how often your model's overfit. Wow, we're just getting a lot of overfit models, really? That's 383. Is it changing? Oh, it's not changing. Because, well, aren't we getting different random samples? Shouldn't we? It's getting the same result. Maybe I'm not storing in different spots, but we didn't get an overfit model the first time. That is taking a different random sample. It might be doing the same randomness. It might be, you know what it might be? It might set the randomness inside of there, and because it's setting the randomness, yeah, so we are getting the same results. And so let me try this. Let me try one last thing to look at here. Set seed 100. And now let's see if we get 383. I want to see if I get that 383 again, which I don't think. There we go. I think for some... Yeah. Did I have another set seed in there? Oh, there we go. Yes. Okay, yeah, that's what it is. So Adam, 1,000 points. What it is this set seed. What's really interesting is set seed, and I don't know if we talked about it that much in this class, but if you do set seed right here, and you say something like 474, and then you go to random normal, and you generate a random normal number. Okay, 302. Okay, so now, watch this. Oops, wow, okay, cool. I bet you, I got it. Okay, I'm going to guess the random normal number. Negative 0.302. I bet you that's it. You ready? Negative 0.302. I just know it like that. So because the randomness procedure was here, when I went back, I was on the same track, as in like I had put myself, I genius. So that's what's going on right there. And so if we were to remove this replication result right here, it would kind of fix the issue too. So now if we want to see like how often we get overfit models, and good job, Adam, kind of noticing that too, because it jumped over my eyes. So now we're doing that model's overfit. That's you see 470. Oof, that was really bad. 349. And we're getting different results now. This model's overfit. It'd be interesting to see what percent of time. We could put this in a for loop. We could see. I think we're doing it. We're doing this last thing right here. What percent of the time do we get an overfit model? Take a guess in the chat. Let's just do this real quick right here. Let's put this in a for loop and see what percent of the time we get an overfit model. Because if we're doing something multiple times like this, closest person in the chat gets 1,000 points. What percent of the time? Adam's guessing a third of the time. You can use the previous information. So what we need to do, we need to put like an overfit percent right here. And we need to store here. And we need to put the I right here. And we'll make the vector earlier on. Well, we are going to store if it's overfit. So we're going to change this code right here. And we're going to do if it's overfit, this will be a 1. And else, if it's not overfit, this will be a what? If it's not overfit, this will be a what? 0. Does everyone see, like, if it is overfit, we will store a 1 in here. If it's not overfit, it'll store a 0. This is, I should have written this as a test question or a homework question. But it's going to run all this code right here. And now we need to go to the start before we do anything. And we're going to go here. And we're going to drop this in here. And then we go before this. And we go to 4. And we're going to run we're going to run 100. Because this does take a moment to run. And this should do it. We're going to take all this code right here, which we have running. And all this code right here is going to go in the for loop. And we know it'll work because we've been running it repeatedly. It should work. We'll cross our fingers. Code, reindent lines, good. And now we go to variable I, going through the vector 1 through 100. And it's just going to continuously run this. Do we have a set seed inside of here? We do not want to set seed because set seed will put us down the same path of randomness. And so we'll see who gets the closest result right here as we rerun these results 100 times to see how often we are overfit. And it should not run that quickly. Error unexpected something and something. Where did we have it? How did we break it that quickly? Else unexpected Oh, really? It's that. I was thinking of the things I changed. Yeah, okay, good. Look at this. Oh, that is so cool. Oh, but wait, is it printing it? Oh, no. Oh, wait. Oh, but we still have it printing it. So I think we're good. It's still doing the test, but no finish. Do we miss something, Adam? We don't need a return because it's not a function. So we don't need a return because it's not a function. It'll be storing into the ith element of the overfit vector. So if it's a function, we need a return. But if it's a for loop, we can just have it doing this right here. And you see it's just checking each model. Yep. Good practice. This is good practice. This is why I'm like, hey, let's just do this example. A lot of fun. Just think about the things you can do if you ask the question, what % of the time do we get an overfit model? And then I'm going to double click this once this is done right here. And it's probably getting close to being done. It's doing one about every second and a half. So it's like 2 minutes of watching it say your model's not overfit, your model is overfit. And once again, the very end of this, if it turns out to be greater than or equal to this, it'll store a 1 right here, or else it'll store a 0. So this last little bit of code right here is the most important line. I could have removed this. It's still just printing to the screen whether or not it's overfit, but we could have removed the last part of the code. Now, what's really great about this is that I did the structure of doing a for loop. What's the first thing we write when we write a for loop? Before we look at this, what's that first thing we write when we write a for loop? We always write our what. We always write our what. Every time we do a for loop, we always write our what. Skeleton, 1,000 points right there, Madeline, big points. We always write that skeleton, 100 points everyone else. Maybe you can get up to 1,000 days, so great job. You write the skeleton. So I already had written the skeleton. So I'm like, I just want to do this 100 times now. So all I did was put something here to store at the end of it. This was all I added, like, hey, after you're done, store this. And then just go through and do this code 100 times. Does everyone see how I got a for loop around this really quickly to say, that code I wrote, just run that code 100 times. And when you're done every single time, just go down here and do this. And here's what we got. And it looks like the 30% guesses are pretty good. 24%. Who gets 1,000 on that? I'm going to throw 1,000 on top. Andrew is the closest. Andrew gets another 1,000 on top of whatever he gets today. So 100 points right there. I love the skeleton. You got it, Andrew. You were right. And so about 22% of the time, and we could have stored the overfitting, but yeah, and we just kind of did like a repeated predictive modeling making. So kind of fun stuff right there. We got the slides open. Let's hop into the slides. So that example right here to start class is kind of like the activity. We'll do an activity tomorrow, so make sure to show up tomorrow for an activity. But these are things we need to practice. We need to practice like how to do our for loops, how to do our functions, and what the heck this code even means. Like, why are we doing this? What did Brian do? Brian wanted to figure out the % of time when he makes these predictive models from this data that he overfits his model. And we saw that 24% of the time, or basically 1/4 of the time, we're getting models that are overfit. That just can just kind of happen with data. It can kind of happen right here. Logistic models and their interpretation. So when we do logistic, we have to instantaneously know that it's a categorical Y. We have to know that. In this class, we are focusing on a two-factor, a two-class level. And you'll see this in the code, especially for the train, is that we're doing a two-class summary. What does two-class summary mean? It means yes, no. I mean, okay, it can mean, like undergraduate, graduate. But then you could simply ask, is someone a graduate student? And the answer would be yes, no. So generally we think of it as a yes, no type thing. A 1-0, Madeline, 100 points right there. A 1-0, like a binary operator. And that's why we can put the probabilities, when you look at the probabilities are on a scale 1 to 0. Because it's like, is it more this? Is it more this? So that's all we're doing right here with the binary operators for the way we're solving this. Now, something that 320 is going to hear a lot, they're going to start hearing at the start of next week, is that we're doing the level of interest. And the level of interest is what comes last alphabetically. So the level of interest is last alphabetically. You just have to memorize that. You'd be like, well, why is it? Just the way the algorithm works. I mean, maybe there's another algorithm in another package that does it differently, but at least in Caret and in R, it's always the level of interest comes last. So if you're predicting if an email is junk or safe, and that's what it is, then what will we predict? We'll give the probability that it's junk or the probability that it's a safe email. What will our model be designed to predict? The probability that it's safe or the probability that it's junk. Safe. Yep. And but you could code your data is an email junk email? Is an email like spam? I know now spam and safe gets more confusing. It would be spam is the level of interest. But you could ask, was the email junk? And if you ask, was the email junk, then the level of interest would be yes or no. Which one of those? If you say, was the email junk, the level of interest would be yes or no. Because you look at an email and say, was that email junk? And then the level of interest would be yes. And you see that kind of works because if you always think of it as like a yes-no thing, and if you're interested in yes, yes is always the level of interest. So the level of interest is last. The level of interest is last. And listen to the alliteration on that. The level of interest in logistic is last. The level of interest in logistic is last. And with indicators, I am first for the reference levels. I teach my 320 students with indicators for reference levels, I am first. The reference level is the first one. Level of interest in logistic is last. So you hear the alliteration on that. Level of interest in logistic is last. Indicators with reference levels, I am first. So if you're doing things like Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, what is the reference level for day of the week? Be careful, we're switching the topic here just quickly. For days of the week, what is the reference level for days of the week? What is the reference day of the week with indicator variables in regression? Friday, Phaedrina right there, 100 points, yep. Because Friday comes first. I am first in reference levels. So I am first. But logistic, the level of interest is last. Put that in the chat right there, first person, 1,000 points. I am first for indicators. Logistic levels of interest last. If you wonder why I make these things up, it's because I have to keep them in my head. And I've definitely said them the wrong way before. And so I am first for indicators, 1,000 points right there. And then I am first for indicators, and that is for categorical X's, categorical X's. And then logistic is categorical Y's. And Madeline right there, 1,000. So if you're wondering what's an indicator, that's a categorical X. What's a logistic? That's a categorical Y. So when you say I am first, that means the reference level for indicators is the first one. That's categorical X's in the model. Logistic, the level of interest is last. That is for categorical Y's. So there's a big switch right here between indicators, categorical X's, logistic, categorical Y's. So just where's your categorical variable in there? So indicators and logistic are both categorical variables, but indicators are categorical X's and logistic is categorical Y's. I can put these on the test in many ways. So we have right here the probabilities, and I should mention this. I think sometimes I think something's so obvious, but then I forget to say it, is that if you want the not level of interest, is just 1 minus. Like, what's the probability? If yes is 90%, what's the probability of no? First person, 1,000 points. I'm going crazy with these 1,000 points today. If the probability of yes is 90, what's the probability of no? Because either yes or no. 10. Boom. Andrew right there. You got 2,000 because you got that secret 1,000 also. Remember, only Andrew's breaking the rules so far. We break the rules some days, though. So we got it right there. You're following along. You're like, okay, if we want not the level of interest, we just do 1 minus. The posterior probabilities are the probabilities after. The naive model is kind of the prior probabilities. It's the overall probability. And the model is going to give a posterior probability after the information we have. And so here's how we make the predictions. We were seeing this yesterday as Brian's brain was just frying itself. It's too much hair. I mean, I'm not going to cut it all off, but it's all the hair, the power. I'm like a reverse, like the more hair, the less. Like, cut your hair now. Go back to being smart. No, I'm not doing it. The hair stays. But we see right here that we would make predictions based on the probabilities. I did mention yesterday that a lot of the algorithms in R flips a coin when it's exactly equal to it. So if we have exactly 50%, the algorithms in R will flip a coin. Traditionally in statistics, we do 50% or more is classified as the level of interest, and less than 50% is classified as not the level of interest. So something is either the level of interest or not the level of interest. And this is kind of like something is either yes or no. And a lot of times yes, no makes sense to just kind of use them right there. Now, the good news is we don't have to solve this. We are not going to sit down and solve this equation by hand. We're just not going to do it. This equation right here solves out for the logit, but we don't want to interpret things like the logit. This equation right here is very easy to memorize how it works. All it is e raised to the regression equation over 1 plus e raised to the regression equation. What is the highest possible number that the regression equation can solve for? What is the highest possible number theoretically that the regression equation can solve for? What is the highest possible theoretical number that the regression equation? The highest possible theoretical number, the regression, and I say theoretical. No, it's a theoretical number that the regression equation can solve for. What is the highest possible theoretical number that the regression equation can solve for? Highest possible theoretical number. A theoretical number that is the highest possible number. Hence, it's not a real number. This number does not exist, but it exists in theory. What's the highest number you can think of? Every kid knows this number. Every kid knows this number. If you're like, they're like, I'll bet you $100, and be like, I'll bet you $1 million. I'll bet you $10 billion. I'll bet you $1 trillion. And you're like, I'll bet you, you know, the biggest number. Who knows it? Someone's got it. 1,000 points. Who knows it? Infinity, paying right. And so it's a limit. Now, what would this equal up to right here? Because that 1 plus, when that kid, truthfully, because when that kid's like 1 plus infinity, you're like, it doesn't, what does this equal up to right now? What does this equal up to? Equals that. What, now we're going to go back. What is the smallest possible number? Infinity, yeah, it's still just 1. What is the smallest possible number right here? What is the smallest possible theoretical number? Once again, theoretical. Boom, Carly, 1,000 points, you're right, negative infinity. What happens when you raise things to a negative? When you raise things to a negative, what happens to those numbers? They approach what? If you raise things to negative powers, remember, it flips it. So things raised to negative powers would approach what? If you keep making it a more negative power, the thing raised to a negative power will approach 0. So what does this equation equal? 0. There's one more interesting spot in this, though. The only other interesting spot is when the regression equation equals up to what? If the regression equation were to equal to what, we'd have one more interesting spot right here. When the regression equation equals 0. And now, this would equal what? E raised to the 0 over 1 plus e raised to the 0 equals exactly what? 1,000 points first person. Bingo, Peyton, great job. And do you know what you just bound this equation by? You just bound this equation, I think it's square brackets, right? Everything in this equation, every number we just theoretically could think of, has to be contained between 0 and 1. And why is this so great? Is because this is for probabilities. Every single number you just gave me is between 0 and 1. So you just showed that this equation right here is bound between 0 and 1. So this logistic curve we are creating, which we can see more complex, it's still just the regression equation for the multiple, same exact thing, nothing new going on right here. This regression equation creates a logistic or sigmoidal curve, and you can even see the 50-50 breakpoint, which we won't focus, that's more in descriptive statistics, but that's when the regression equation equals to 0. So if the regression equation equals to 0, you would predict a 50% probability. And that has to kind of deal with the intercept. That's more for descriptive statistics. But just understanding that this model has to be bound by 0 and 1. There's no possible way for this equation right here to solve anything outside of the bounds of 0 and 1. Every single thing, because this is just e raised to some number. I mean, you're like, but wait, isn't it e raised to this plus this times this plus this times this plus this? Let's just e raised to a number, because this will all solve out when you plug in the values of x's. It'll be this plus this times this, and that'll just be a number plus this times this, and it'll just be e raised to a number over 1 plus e raised to that same number, because it's always e raised to the regression over 1 plus e raised to the regression. And once I realized that about logistic, I was like, wait, it's just the same thing we are doing in regular old regression. Who's like, wait a minute, logistic? Who has that like thought right now? Like, wait, this is regression, and that's logistic. It's just e raised to this equation. Just so you can see specifically, this equation right here is just e raised to that equation. And then it's just over 1 plus e raised to that equation. And that creates this kind of logistic curve. And I will say this, maybe Nitin's seen this a lot, especially in like differential equations. You've got so much e. E is used, Nitin, you got my back on this? E is used like all the time. Euler's number. Is that Euler's number? 2.71828, 2.71828, 1828, 459, 4523. That is like used all the time in differential equations. Like differential equations just loves E. I loved E until I did differential equations. I was like, I've had enough. I've had enough of that number with natural logs and all that good stuff. But it creates some interesting curves. It creates exp is one of our favorite functions. Yeah, right. I know, right? 1,000 points right there. And it really is a very, all the things we figured out in mathematics is so cool. We figured out so many things. And probably one of my favorite proofs are the easiest things to understand. Okay, wait. I want you guys to tell me this. Here, let's do a vote in the chat right here. Let's do a quick math vote. You ready? Here's our quick math vote of the day. We're taking a math poll. So the question is, 0.99 repeating is equal to 1 or not equal to 1? 0.99 repeating is equal to 1 or not equal to 1? Get ready to vote yes or no. 0.99 repeating is equal to 1 or not equal to 1? Let's take a poll with a yes or no. Do I have a yes or no in here? I do. So 0.99 repeating is equal to 1 or not equal to 1? Vote yes, vote no. 0.99 repeating. You gave it away, Nin. I like the emphatic yes. Yes, it is. And there's a really, if you're wondering, there's a way to figure this out very quickly. It's one of my favorite things. And so you might be wondering, how is it yes? We'll go ahead and close the poll right here. Stream ups. I'm asking, close poll, stream ups. There we go, complete poll. Okay, so if you're wondering how that works, are the polls case sensitive? Actually, I don't think they are. I think just the singular Y was not counted, but the lowercase and uppercase were counted. So if you look at how many votes there were, 1, 2, 3, 4, 5, 6, 7. Yeah, it's interesting. Maybe it counted that it might have. I don't know. I have to look at how many votes there were, but I think it's not case sensitive. I think we've noticed that the polls aren't case sensitive. And you might be wondering, okay, how is this? Well, watch this. What is 1/3? 1/3 is equal to 0.333 repeating. What is 1/3 times 3? 1/3 times 3 is 3 over 3. So since that's 3 over 3, 3 over 3 is equal to 0.99 repeating. But isn't 3 over 3 equal to 1? There you go. There it is. And just think about it as a limit. Like it's going to achieve that because theoretically numbers are carried out infinitely. So you can't be like, well, I don't know. I like to think about these types of things. I'm maybe just too nerdy for my own good. But the number, you can't be like, well, you can't reach an infinite series, but the number exists as an infinite series. So the number achieves the infinite series even though we can't add it up. So the number itself will be added. Does that make sense? Am I explaining this properly? Hopefully that quick proof shows it off, that 1/3 is 0.333 repeating, and 1/3 times 3 is, and you could even do where, 3/9, but hopefully, because that's 0.3333 repeating, and then 9 over 9 would be 0.999 repeating. All repeating decimals or fractions, vice versa, yeah. It's kind of cool just to, I really like math. I wish I had gotten into the high-level mathematics to understand like the in-depth, like real analysis and all this stuff. Hey, one of these days, maybe maybe I'll go back. It's yeah, one of these days maybe I'll finish off my understanding of mathematics. But it's once you stop using numbers in mathematics, that's when my brain hurts. I'm like, let's use the numbers. And they're like, no, you can't use numbers. No more numbers. I'm like, but that's what math is. And they're like, no, math is ideas. I love it. I love education. So okay. So one of these days, I don't recommend abstract things. I know, right? I know. That's why I do the things I do. Okay. So let's talk about some more stats. Let's talk about what Brian knows. Because yesterday Brian showed that his math was broken, but Brian fixed his mind. Brian got everything up here fixed up, so we're good. So the problem is all models are wrong, some are useful. If you notice right here, this is how good a cake will taste as we increase the baking time. So a cake is going to taste better and better and better with the logistic model. The logistic model does not take into account the kind of decrease that would happen here as we overbake the cake and turn it into a hockey puck. You don't want this. There are ways to twist the logistic model like that. So there are ways with polynomial terms to create a polynomial logistic model. Once again, the equation still must solve at the top for some number between 0 and 1, but the relationship is no longer monotonic. What does Brian mean by monotonic? It means goes in one direction. All basic logistic models with non-polynomial terms will be monotonic, but you could technically add a polynomial term which would give you that second change to the model. You could do a third order, which would make it go back up. We don't focus on it that much, but here's the thing. When you do your variable selection, gotta hop over to the main screen, you could check for polynomial terms very quickly in your model by just going and, oh, I guess we might have to create the squares of the variables. You could do variable creation. To do variable creation, you would go here to salary, $ education, and you could literally just square it. And you could go here. So now we can do a square of this and include this as a polynomial term. So now inside of the salary data frame, we have the square of somebody's, did I do salary? So education squared. So now I have a variable of education squared, and that's one way to just include it. So we could start including different variables in the model that are the squares of certain things. There's lots of ways to do it, and there's lots of ways to add in these variables. And I say this because variable selection is one of the hardest possible things to do in making the best models. And this is why Kaggle, like, to think this stuff is easy is to neglect that there's a site Kaggle with 5,000 different people who understand how to do these techniques, all competing to make the best models. Is any one of their models right? No. All their models are probably pretty good, and then Kaggle judges by which model is the most useful. So when you think about this, you're not going to, there's no right answers in statistics. And that's probably one of the things I like about it. Statistics is about it's more about finding an answer and then explaining why your answer is good. You're not going to be like, I found the right answer. You're going to be like, here's why my answer is good. If you're making an equation that explains how to make a good cake, is there a right answer to that? No. But there is some sort of maybe formula that's like, okay, you should bake it for this time, you should do this, you should do that, and then people can debate over what the best formula is for making the cake. There's no right answer to it. I mean, theoretically there might be one, but we're not going to really, it'll be hard to say. So when we do logistic right here, the coefficients in the logistic change the probability. So, and you can see, here's talking about the probability changing. So a lot of times things are in the notes that I've kind of already mentioned, but what we're talking about is kind of an increase to the probability or a decrease to the probability. When we have two individuals, we'd expect them to differ in their probability, where the cake, these are the two individuals, where the cake that has the higher baking time is expected to have a higher probability of liking the cake. Two cakes that differ in their baking time by 1 minute, the cake that has been baked for longer has a higher probability of being liked. But the problem is, of course, that this model suggests just leave the cake in the oven all day, and then everyone will love the cake. But there is a non-monotonic relationship to this, so this model is not really a great representation of reality, especially if we were to go outside the bounds of the model. Here we go. Here are the coefficients. Once again, this is in the notes, and we can interpret as many coefficients as we want right here. And this is just a lot of review right here about how to interpret coefficients and what it means and why we would not mention the coefficient value. Now, I want to make this very, very clear. In regular regression, the value of the coefficient is constant, as in two individuals who differ by x in 1 unit are expected to differ by y in blank units, and that is constant no matter where we're at, unless there's an interaction. But in logistic, the difference here is not constant. But if we are just doing logistic without higher polynomial terms, it is true that two individuals who differ by x in 1 unit are expected to have, two individuals who differ by an x unit, two individuals who differ by 1 unit of x, the individual with the higher x is expected to have a higher probability for the level of interest. And this is when the coefficient is positive. If it was negative, two individuals who differ by 1 unit of x, the individual with the higher x would be expected to have a lower probability because it would be sigmoidal down. And we can see that back here in the notes. If the coefficient of the x was negative, we would have a curve that looks like this. And then two individuals who differ by 1 unit of x, the individual with the higher x is expected to have a lower probability. And it's true for all points that if you move forward on this line, it'll keep going down like this. Very important to understand this. Who are otherwise identical? Yes, 1,000 points initial right there. in a multiple, which this right here is a simple. So this, since it's a simple, we don't have to say the otherwise identical. But if we have a multiple, which these are still simple, it's just showing the mathematics for you. And once again, we don't want to talk about it as cause and effect, but we do have a multiple regression right here. If we are doing a multiple, then we need to make sure who are otherwise identical. And that is so key, because we're saying like two cakes that differ in their bake time by 1 minute, but are otherwise identical, like they have the same, they're the same type of cake. Because think about this. If we were to say two cakes and we didn't say otherwise identical, maybe we're talking about an ice cream cake. Maybe we're talking about a cookie cake. Maybe we're talking about a cheesecake. And all those cakes, especially an ice cream cake, have different bake times. But what are we saying? Two cakes that are otherwise identical, where they differ in their bake time by 1 minute, the cake that is baked longer is expected to have a higher probability of being liked. So if we have a curve like this, which is the red curve right here, our model, it would suggest that two cakes that are otherwise identical, if it's a multiple model, who differ in their bake time by 1 minute, the cake with the higher bake time has a higher probability of being liked. We predict it has the higher probability of being liked. Does that make sense, Anisha, right there? If it's a multiple model, we do need to say otherwise identical, because that would hold the type of cake constant, that would hold other things constant about it, to say, okay, everything else the same. If the cake is baked longer, it has a higher probability of being liked, or we would predict it to be more liked. There we go. And once again, that means there's so much theory to this. That doesn't mean that that individual cake would be liked by that person. It means that if we infinitely gave cakes over the long run of repeated trials, that cake would have a higher probability, like over repeated trials on average. Everything is so theoretical on what it means, and that's the hardest part about these topics sometimes, is we're not saying like that cake will be liked. We're saying repeated trials with that cake would show a higher probability of being liked. So many things. So if this right here, if the coefficient is positive, it'll increase the probability, or we would say it would have a higher probability. If the coefficient is negative, then the probability would be less. Do not worry about this. This will not be on your test. But once again, we can figure out where we would have that 50-50 breakpoint, and we focus more on that in descriptive statistics. There's some of the mathematics. Just like in regression, the equation of logistic is not a physical law. Do not say things like, and I will probably put things like this on the test, that if the cake is baked longer, it will be liked. We're saying two cakes that differ in their bake time by 1 minute, the cake that is baked longer has a higher probability of being liked. And if it's multiple, two cakes that are otherwise identical that differ in their bake time by 1 minute, the cake that has a higher bake time is more likely to be liked. It's a higher probability of being liked. We're not saying it will, it just has a higher predicted probability. So it's not like people will like this cake more. We predict that people will like this cake more. So do not treat it like cause and effect. And so here we are with our logistic model. We're predicting the probability of purchase. So we should know how to interpret every one of these coefficients. So we expect, boom, Sarah, 1,000 points right there. Exactly. We would expect. That's a great way of phrasing it, not will. And I always kind of put that on display in 320. Like I'll say things like, it will do this. No, that's cause and effect. We expect this. And expect is fine. Predict, expect, on average. Those are key words we can sometimes throw in there. You don't need all of them. You wouldn't say, I would predict that we expect that on average. That's kind of overkill. As soon as you say we would expect, you're not saying it will happen. You're just saying the model predicts. Like it's another synonymous way of saying I expect this, model predicts this. And that's fine. You expect this to happen. Well, that's what we expect because the model predicts it, which means it would happen on average. And so right here, we see that we are predicting, will someone make a purchase? We have here tenure. Tenure is a quantitative variable. How do I know tenure is a quantitative? Because whenever you have indicators, you will see the level of the indicators right here. So how do I know that tenure is instantly quantitative in this output? It's because we have, it covers exactly. Good job, Jordan, right there, 1,000 points. Checking balance, or checking, ooh, is that a, let me look at it. Because checking balance, I just made a mistake. Checking balance is also a quantitative variable because there's not checking with level balance. It's tricking me there by putting that capital B right there. And I think this is the, why can't I think which data set this is? This isn't the, no, it is the census data. It should be census data. Let's hop over to the data sets. We should put what data set it is right there, but that's the census data if I am correct. Data census, and let's look at we're going to load up dplyr for the moment. Dplyr, because dplyr has a really great function, glimpse, and with glimpse you can view something and take a quick look at it. And we see here response rate, urban, suburban, rural, and this is a different data set. Which data set is that? Why would we do that and not mark the data set? Tenure, checking balance, homeowner, and then it's got area classification, which I was thinking because this has area classification right here with urban, suburban, and rural. I'm trying to think, we should have what data set this is. Predicting a purchase. Well, checking balance is a quantitative variable. So let's hop back right here. And checking balance is quantitative. It's just the way it's spelled, because usually when you have an indicator, you see it right here. So there's not the quantitative variable homeowner yes. But what are the only values that homeowner can take on? Homeowner yes can only take on the values of what or what, and it's kind of giving it away right here. Homeowner can only take on the values of what or what. And this is a review now. These are key things. Homeowner can only be a this or this. Homeowner yes, specifically. Adrian right there, great job. 1,000 points, you're at the thousands right there. It can only be a 1 or a 0 because someone's only a homeowner yes, and if they're a homeowner yes, then they're not a homeowner. Then they're not a homeowner no. That sounds weird, but either they are a homeowner or they're not a homeowner. And if we put a 0 in for this, they'd be not a homeowner. Then we have right here LMNOP good. And so right here, we have right here, if we put a 1 for this variable, which would be this whole thing, let's make it sure. If we put a 1 right here for area classification U, then they are urban. If we put a 1 right here for area classification suburban, they are suburban. But I gave it away just a second ago. If both of these are 0, then they are not urban, and they are not suburban. They are what? They are not urban. They are not suburban. They would be what? I know, right? I get so many tell markers. I hate that. They would not be urban. They'd not be suburban. They'd be what? Because if you put a 0, then they're not that, and they're not this. Rural. Yep. Because they're not any of the, they're not either of those. So this is where I'm talking about indicator variables. These are the indicators. And then the reference level. Why is rural the reference level? This is a review question now. Someone gets another 1,000 on top of their 1,000 today. Why is rural the reference level? Why is rural the reference? And you heard me doing it earlier. It's like, oh, MNOPQRST. Okay, good, yeah. So I was like whispering it. First alphabetically, Jordan, you're right. Yep, that's why rural is the reference level. And indicators deal with categorical X's, where logistic deals with a categorical Y. Does everyone see the key difference right here? That logistic deals with the categorical Y. So since this is predicting probability of purchase, it's logistic regression. We will be predicting the probability yes that someone purchases. And you can see it's kind of giving it away that tenure is quantitative, checking balance is quantitative. Homeowner is a 2-level categorical. In area classification, it tells you right there. It tells you what the things are with rural, suburban, and urban right there. So hopefully this all makes sense with this output and what we have going on right here. The estimates are the weights of the coefficients in the model, and the standard error is our uncertainty. The z-scores are a standardized measure of how much the estimate is, and the p-value is whether or not they are significant. A lot of this goes to descriptive statistics, though, so we will not focus on it too much in this class because we're not going to describe what's going on. We're going to predict whether someone will make a purchase. Basically, the question for the company wouldn't be who makes purchases is descriptives, and then who will make purchases is predictive. Like let's try to predict whether or not this customer will make a purchase, and then we might make a plan of action, and then that goes to what? 1,000 point on top of your 1,000. We have right here, who are the people making purchases? Descriptive. Who will make purchases at our company, from our company? Predictive. How should we market to these people? What would that be? So what's that last part right there? How do we market to these people? What marketing should we do for these people? We've got like, here's prescriptive. Nice job, Jordan, right there. Yep, prescriptive. So when you go from descriptive, who are our customers making purchases? Like, can you explain to me like what these customers are like? Like, do they have tenure? Do they have checking balance? And that's kind of what we're looking at here is the descriptive statistics. Who will make purchases? Like, can you predict if a future customer will make a purchase? Predictive. And then how can we like market to people based on our understanding of whether or not they're purchase? that gets into prescriptive because it's a course of action. We're saying like, what action should we take? Like a prescription. Just think, I know, right? Jordan, great job right there. So here's Sarah. You were second, right? Vadrina, Sarah, and Jordan, you guys are at 2,000. So keep it up. I want you guys to keep, like, I love it. Even if you have the points that you're still responding, I want you to keep doing it. And just summary. If X is a numeric predictor, once again, we have this right here. So make sure you know how to interpret these. These are just like review slides. I've been doing a lot of these today. Here, I'll do the interpretations, which are basically on the slides. So you can see me doing them. Where'd it go? Okay, here we go right here. Two individuals who differ in their tenure by 1 year of tenure. The individual with the higher tenure is less likely to make a purchase. Two individuals who differ in their tenure by 1 year, I think that's the units of it. The individual with the higher tenure is less likely to make a purchase because the coefficient is negative. Two individuals who differ in their checking balance by $1. Sure, it's a very small coefficient if you look at it. Two individuals who differ in their checking balance by $1. The individual with the higher checking balance is more likely to make a purchase. Two individuals, this is going to be a change because it's a categorical now. Two individuals, Anisha should have caught me, who are otherwise identical, but one individual is a homeowner and the other individual is not a homeowner. The individual who is a homeowner is less likely to make a purchase. And why are they less likely? The coefficient is negative. Two individuals who are otherwise identical, where one individual lives in a suburban area and the other individual lives in a rural area, because rural is the reference. We're going to compare it to the reference. Two individuals who are otherwise identical, where one individual lives in the suburban area and the other individual lives in the rural area. The individual in the suburban area is more likely to make a purchase. Why is the suburban more likely to make a purchase? Why did Brian say the individual in the suburban is more likely to make a purchase than the rural? Why did I do that? Well, the rural is the reference, and then why is the suburban more likely than the rural to make a purchase? Remember, we're predicting yes because yes is the last level. Because it's positive. Coefficient is positive, makes more likely. So, and you don't have to interpret the value of it. You just say they're more likely. It's not like they're 9% more likely or 0.09 or 0.009. It'd be 0.09. But don't worry about the size of the coefficient. You just look at it if it's positive or negative. That's all you look at right there. Two individuals who are otherwise identical, where one individual lives in the urban area and the other individual lives in the rural area. The individual in the urban area is more likely to make a purchase. There we go. Interpretation of coefficients. And that's all through the notes right here. Just showing you what's going on. Regularized logistic. Can we also say the difference in Y among two otherwise identical nodes between close? Write out, you might need to write a full interpretation. I could look. If you write it fully, I'd take a look at it. So, and a student asked me a long time ago, they say, well, why do I have to repeat what you say exactly? And I said to them, because I've seen a lot of mistakes. I've seen a lot of things that just don't sound correct. And Dr. Petrie kind of wrote this to be very exact. Like, he's like, what exactly does it mean? And I always go back to the kind of like predicting somebody's body fat. We're not saying like, when you gain weight, your body fat will decrease. We're saying two individuals who differ in their weight by 1 pound are expected to differ in their body fat by this. And it's not saying, you have to be careful because you're not saying like, it shouldn't sound like a change, because we're not saying if somebody, here's a really bad interpretation. This is a horrible, do not write this down. I might put this on the test as a false answer. People who go from urban to rural are expected to have a change of this amount. There's so many bad things. One, we're not talking about the same person going from a rural to urban. That right there makes it wrong. We're not saying if somebody goes from rural to urban, and then we don't want to say change. Like the idea of it changing, no, we're talking about two individuals. For example, the difference in total lifetime value to a company among otherwise identical customers between males and females is $97, with males being higher than females. I think that's super close. I'm going to change one thing. The difference in total lifetime value to a company among otherwise identical customers between, just say the expected difference, Jordan, I think that's right. The expected difference in total lifetime value between other, so just change it there. So when you say the difference, it sounds, I know it's kind of, it's like, it's just like adding an exact word. I would just say the expected difference. No, that was good. It was good. That was a really good answer. I would just say the expected. That's all I would change. That's a totally fine answer, and I don't want to turn people into robots. I want people to have their own thoughts. But I would just say expected difference. The expected difference for a company with two otherwise identical individuals. Yeah. And then the otherwise identical is key too, because we have to say every other variable is held constant. Like everything else held constant, here's the difference. And it goes to a very mathematical way where we're just literally changing this by one unit. Like we're saying if there exist these two individuals, we would expect them to have this difference. So it's very mathematical in what it says. So it's like in math, it's exact because math is like numbers. So when we do regularized regression, what is the goal of regression? Well, this regression right here is only optimizing on what? 1,000 points on top of your points. Who's going to get up to 2,000 today and break the rules? When we're optimizing this right here, what are we only optimizing on right here? What are we only optimizing on with this? Like, there's two things we optimize. So this is linear regression. And what is this that we're trying to minimize with the linear regression of our so I'm asking for like a keyword that if we're going to regularize, we only, without regularization, kind of, I should bias. Yeah, this is the bias. This is how much the model misses by. So this is the bias component. And we sometimes think of bias as root mean square error. So we have this right here. We're going to have to do a switch in logistic to talk about the maximum likelihood ratio and all these things right here with our estimates. So the coefficients are chosen according to the maximum likelihood ratio, which is going to try to optimize how our model is chosen. So we do not have to worry too much about this. I kind of consider these bonus slides. Do not worry too much about this, but it's going to create a curve that goes through our data as best as possible. It's literally just going to try to make coefficients that go through our data. I think of it, let me show you what the visual I think in my mind is, because maybe it'll help you to look inside my mind. So when we have logistic, we're predicting if something is yes or no. And so you have these dots right here. And these are whether or not someone makes a purchase. And the black dots are making a purchase, the red dots are not. And the way the logistic curve works is the logistic curve tries to fit through here. That at all points, if you were to take a random subset of points, like within this window, the probability that the logistic curve is putting out should estimate at these random points accurately the percentage. So the logistic curve is trying to accurately take and mimic these. And that's what the maximum likelihood estimates are trying to do, or MLEs as we call them sometimes. They're trying to create the estimates that best replicate the percentages at all points. And that's what you see in the slides right here, is that we're trying to, at all points, create the estimates that best go through the model. So we're trying to create this right here so that at all points, we get the proper probabilities right here. And I just kind of always see this visual in my head right here, that this curve right here is trying to, at all points, trying to optimize. Because think about this. This is basically like a what? This curve is trying to predict the percentages accurately. This is just like what? It's just like it's trying to make the what's very small for this. Someone said it earlier. This is, if you're looking at just the red line, it's trying to make very small what's. By accurately predicting the percentages at all times, it's trying to basically get very small what's. It's trying to get very small residuals. Sarah, that's worth 1,000 right there, yeah. It's basically trying to, which is the bias. It's trying to get the percentages correct at all the points. And it might be very hard because you will have data that just does not follow the logistic curve. You could have data that there's a non-monotonic relationship with. That's horrible. You see, it's so weird. I clicked that and it does that. You could have data that, does something like this right here, and does this, and does this. And so when it fits the logistic curve right here, it's going to fit a logistic curve that's not going to be perfect. These are all points, if you can't tell. And the logistic curve it fits is probably going to be something, well, doesn't fit like that. I don't know, something like that. But the logistic curve, obviously now, and it needs to be sigmoidal, so it needs to go, there we go. That's a sigmoidal curve. But if you notice, the curve is going to have problems in certain areas. So these are basically your errors because it's not replicating the percentages, but the way in which the mathematics is chosen is trying to minimize the error it makes on the percentages it estimates. Does that make sense? How these are basically residuals. Like this area right in here is where you have your biggest residual. Like this is where the model's really making mistakes. The model is inaccurately predicting right here because it's not replicating the percentages we see within the native data. So that is basically the analogous to the linear regression. And how is this curve chosen? This curve is chosen, like before we were trying to minimize the residuals, and now we're trying to replicate the data and get the percentages that the model predicts as close. And how do we do this? And this is the only thing you really need to know. We do this by creating maximum likelihood estimates. And these maximum likelihood estimates simply put the coefficients of logistic regression and thus the shape of the curve are selected so that the resulting model has the highest chance of replicating the training data. So, everything I'm trying to show you right here is that the way in which we pick these coefficients for the model, which dictate the shape of the curve, are just to make a curve that replicates the data. It replicates the percentages. So whatever percentages we see throughout the data, these percentages would be chosen, and we're going to pick the estimates in the model based on this. So not too much right there. It's just kind of understand what's going on. And now we get into, well, it does not mention the regularization. What's going on? I mean, it's pretty easy to understand what regularization is. What two methods of regularization will we pick? There it is right there, because it's that simple. And we were already doing it today. So what are the two methods? You might say, wait, Brian, there's three. I mean, there is. Lasso and ridge. Ridge takes the squares of the coefficient and try to minimizes the sums of the squares of the coefficients. And lasso tries to minimize the absolute value of the coefficients. And then what is GLM net? That's what we saw at the beginning of class. GLM net is the mixing of lasso and ridge. GLM net is the mixing of the lasso and ridge. So GLM net is just a mixing of lasso and ridge where we can mix a certain percentage of it. And so we covered that a lot this week. We've done a lot on regularized regression this week. Pros and cons of logistic. I think this is pretty much review. I'm going to see if there's anything in assessing. Yeah. And we should look at this. Okay. Logistic regression can be very powerful with the right set of predictors. The problem is variable selection. We're going to let this do it for us. It is very slow. These models take a longer time to fit. This doesn't really make great test questions. Don't worry too much about that one. Pros, best model with probabilities changed in accordance with the logistic. Useful for descriptive analytics. We won't do much of that. Been around a long time. People are comfortable with it. The logistic is kind of classic. So make sure you have a decent understanding of logistic. Because I remember when I was first doing it, I was like, what the heck's logistic? It's just predicting a categorical Y. Probability of 0 and 1, or between 0 and 1. It's often hard time to tune these variables and can be really hard for people to understand. And you just see that when you get this jump from linear to logistic, as I had in undergrad, there was this like, wait, what are we doing? What's going on? And really, the last part here, the assessing of the classification models, is what we did all last class. All last class, we focused on assessing classification models. What are the two ways in this class that I will have you assess a classification model? 1,000 points, first person, name the two ways that we will assess classification models in this class. There's about 5 ways I can think about. Because there's always more ways in statistics. There's always someone coming up with a new way to do things. But there's some classic and kind of ways that people use. What are the two ways that we will assess how well our logistic model does? Boom. Accuracy and AUC right there. Boom. Exactly. And you see that by how we set up our fit control, wrong button. You can see this immediately in how we're setting up our fit control all the way up. All those untitled. Where's our fit control setting up? Fit control. Yeah, we'll go. There it is. Here it is. All the way up here, we have the fit controls right here. And we have one tuned to accuracy, and we have one tuned to AUC ROC. So once again, this is you just call it that. So that's the AUC right there, and how you tune your model will set it up. Why? Wait a minute. This whole model over here that I was doing all today, I wasn't getting AUC though. Why wasn't I getting, these were all, they weren't AUCs. Why, this is not an AUC. Because that can't be an AUC. Because it area under the curve can only be between 0 and 1. That can't be an AUC. Why was this model earlier? And where's the hint at? I don't see it. Wait, the hint is right there. Why is this number right here not, why is this, wait, what's going on? What's going on right here? That's not an AUC. The first example from today was a what variable. So it can't be AUC. We can't tune it on AUC because this is the things we need to know like pretty quickly. The first variable we did today when we were making a model was a 1,000 points, who knows? That first variable was a what type of variable, which means we're doing something very different. It was a quantitative variable. That first variable up here was quantitative, which means my fit control. So it's a quantitative which controls. Does that make sense, Sarah? That since the variable I did at the start of class was quantitative, I'm going to fit on just kind of a RMSE. Couldn't think for a moment. We're going to fit on RMSE because RMSE, and you could fit on MAE, so you could if you wanted, but we're going to fit on RMSE, and we're going to find the model that has the best typical miss. So this is the hard thing for people. Yep, is that this switch that happens, because if you're doing logistic, you're doing something different than linear. So that's why I'm trying to, I know I'm switching, but your brain has to like just switch. When you do logistic, it's like, okay, now I'm predicting probabilities and I'm tuning on AUC, which I usually tune on AUC, or you could tune on accuracy if you really wanted. Okay, now I'm doing linear, I'm tuning on RMSE, which is the typical miss. And these are the things I see people make mistakes on the test, because I'll switch what the model is, and then you have to know, am I doing a categorical or a quantitative? And here's the thing, we've got like 2 more models to cover for this class, and everything I'm telling you right now is important for assessing a quantitative or categorical model. And here's the assessing the categorical. So when we assess categoricals, we need to have some sort of method of doing it. And we can compare it to the naive model. Previously in quantitative models, we had the RMSE. Our number one best way, in my opinion, is going to be the AUC for categorical. So here's quantitative and here's categorical. I do think this is the best method, but still your boss might want to know what % of the time are we right. If your boss asks you what % of the time are we right, what would you report to them of the model? If the boss said, how often is your model correct? You would just report the this of the model. So if they said, what % of the time is your model correct? You'd be like, oh, it's got this blank. It's 90% what? Kind of true. 1,000 points right there. Yeah, you're at the 2,000, I think. What would you, if your boss says, what % of the time is your model correct? You would just look up your what of your model. What % of the time does your model make correct predictions? Yeah, 3,000. Nice job. What % of the time does your model make correct predictions? One of the things we said that we can measure our model by is it's not AUC, but accuracy. So I'm switching the topics on you. Accuracy is what % of the time we make correct predictions. Does that make sense? AUC is what % of the time our model gives the yes class a higher probability than the no class. Big review from yesterday. We got it right. Watch the end of the video. We ended up showing everything was correct, and Brian just can't draw. Brian can't draw. Don't ask Brian to draw. So the AUC is what % of the time the yes class receives a higher probability than the no class. AUC is what % of the time the yes class receives a higher probability than the no class. And we showed this. Watch at the end of class. We went on for like 20, 30 minutes more. If you want to review that, we went very exact and we did a lot of examples. And then we were predicting the answers multiple times. So who stayed for that extra 20 minutes and feels like they understand AUC pretty well? I know a few people were there. I don't want to like call out names, but did anyone stay after it and then watch that and be like, I think I get what's going on with this? Because AUC is one of the hardest topics. Even I made a mistake yesterday. I did, but not 100% good. Yeah. And so AUC is what % of the time the yes class receives a higher probability than the no class. And one of the key examples I like to use when I teach that, which I've taught it multiple times, sorry, my brain overheated yesterday. You guys, I'm so sorry. I felt so bad. And the more I felt bad yesterday, the worse it got, because the more like my brain just kept being like, you got this. I'm like, no. So, and I haven't had that happen in like a year or two where my brain melted. But Andrew's kind of right. Um, but the key example I always use for that part, because I've got key examples I use when I teach these things, is my sister trying to do, I like it right there. My sister trying to do marketing. My sister, if we had a model that was only like 80% accurate, I like that right there. If we had a model that was 80% accurate, that means the predictions it makes is correct 80% of the time. But if we have a model that has an AUC of 1, that means all the yeses have the highest probabilities. If the model has an AUC of 1, all the yeses have the highest probabilities. So if I made this model for my sister with like 10,000 clients, and if I tune it on AUC, it'll focus on trying to get the yeses, the actual yeses, to have the highest probabilities. And if I achieve an AUC of 1, she could literally just start going from the top of the list down. I probably wouldn't get an AUC of 1, but she could go from the top of the list down, and it would be like yes, 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 yes. And as soon as she hits a no, she'd be like, okay, I'm done with the yeses. Now, this might be on new data, so she wouldn't know for certain. But if you tune on AUC, it's going to focus on getting those yeses at the top of the list. It would not hurt a model. Like, just to show it again, let's go back here. Do we still have the, whoops, wrong button. Keep putting the third button. It would not hurt the model. And we'll show it here, right here. That's the thing. There we go. So if we have, and we should be able to do the PROC of it. Yeah, so I think let's do library PROC. Don't be weird, computer. And ROC is the code, and ROC should take, I think it takes the actual and the predicted. So if we have right here, so wouldn't that be bias? So the bias of the model is going to be how far off the like percentages are. And so we are measuring the bias of the model on how well, like the bias would kind of be measured by the AUC. And then we don't want to overfit to AUC so that it works on new data. Sarah, 1,000 points. You're pretty much right there. So, but then how do we measure how well the model does? And then how much do we say we are going to take for the weight of the coefficients is the variance. So the variance is going to be controlled by how much penalty we put on the weight of the coefficients. Really good question, Sarah. Great job. I love it when everyone's, so let's do the actual. So this right here, and let's go prob. And so this was what the examples we were doing yesterday, and this is just a very quick example of it. Now, if you notice, there we go, unexpected, where did I do it? Oh, ha 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 ha. There we go. And it should be, it takes, the probabilities are second. Wait. Actual, comma, prob. Yeah, there we go. Perfect. This model does not have an accuracy, and I can change it right here. I could change it to this. This model does not, either way I do it, does not have an accuracy of 1. What is the accuracy of this model? This should be a very simple test question right now for what is the accuracy of this model. What is the accuracy of this model? If you've been following along all lecture, you should be able to be like, the accuracy of that model is this. What is the accuracy of that model? 1,000 points first person, who knows? What is the accuracy of this model? 66%. Because if you were to go here to predicted, the predicted for this model would be yes, yes, and yes. Whoops, not a capital yes like that. Why do we predict this is a yes? Why do we predict that this is a yes? And why do we predict that this is a yes? Why are we predicting, even though this is no, which means we get it wrong? And you can check the, see now my brain's working there. There we go. Why would we predict that this would be yes? Because anything with over a 50% probability is predicted to be yes. But when you look at this right here, you need to then think about how the AUC works. And here's the code for AUC right here, because ROC gives you the AUC, because then it tells you the area under the curve. So AUC is area under the ROC receiver operator curve. And so why is the AUC 1? Even though the accuracy is 66%, the AUC is 1 because with an AUC of 1 right here, we have that 100% of the time the yes class receives a higher probability than the no class. And we can fiddle with this to show how AUC works. And we should be able to do this right here. And we should be able to figure out the AUC now. Who here, and I have them in order, you get 5,000. No, I know. I did one of these in earlier class. Who here for 10,000 points could figure out the AUC on this pretty instantaneously? You better bet this is going to be on the test. Oh, I think Nitin got it. Let me see. Yeah, Nitin, I think you're correct. Because that's 100 and that's 50, and 50 divided, yeah, it's 75. You're like, I got this. Yeah. Boom. 75% of the time, the yes class receives a higher probability than the no class. 75% of the time. Do you just find... I was finding the percent of time that the... Sorry, Sarah, rephrase your question. Make sure that AUC is a little bit more complicated. If remember, review yesterday's class, reviews today's class. Hopefully, if you understand AUC, problems like this right here should be pretty quickly to understand that 75% of the time, the yes class receives a high probability than the no class. And I might go back to the notes. We did this a lot yesterday. And once again, my brain was kind of like breaking and slowing down. But if we go right here, so this should go up, over, yeah. To draw this out and watch this, we can draw it out right now. We can draw it out. We can show how to draw it. The way to draw this would be the following. We go like this, and we go up, over, over. And guess what? What percent of the curve have I shaded? What, and here's my random chance curve. So what percent of the curve have I shaded again, Nitin, right here? Not under the random chance. But what percent of the curve have we shaded right here by doing this? We've shaded exactly 75. Boom! Look at that. That's a speed run of AUC right there. Red Bull. This class is sponsored by... It's not sponsored by Red Bull. That's a joke. But we should be able to understand how to draw these things. Sorry, once again. I'm going to stop apologizing for yesterday. I really felt bad, you guys. I don't know. Gives you wings. It definitely. So we should be able to... once again, I can't have you draw it. That'd be insane. That'd be awesome. And so we'll hop back here to the notes right here. Oh, yeah, okay. Let me show you that. Yeah, let me show you that. Sure. Please ask. Let me hop back there. Okay, so how do we get the 75% right here? You literally have to look at this right here, and we have to say, let's look at this yes. Okay, does everyone see we're looking at that? Yes. And I have them ordered right here by the probabilities. Does everyone see I have the highest probability down to the lowest? That makes this problem a little bit easier. I'm not going to throw a trick. I'm not going to reorder them on the test. I'll put them in order because I don't want to make a second step and be like, I tricked you. I didn't put them in the order. So I put them in order. That helps with figuring this out. I'll show you a trick here at the end. Like, I won't put a trick on the test though. So just tell me, when you look at this yes, and this no, how many times out of how many times does this yes have a higher probability than the no? Great job, Jordan, right there. How many times does this yes have a higher probability than no? So see if you can figure out that one. And Jordan's got a great explanation in the chat. Jordan, you're at 5,000. Jordan, you got you at 5,000. That's a great explanation, Jordan. Crazy points. 100% of the time, or 2 out of 2, which is 100% of the time. Does everyone agree? That is 2 out of 2 times. Are we good on that? 2 out of 2. Let's look at this yes right here, which is associated with this probability right here. This yes right here, which I do have in the correct order, this yes right here gets a higher probability than the no's what percent of the time? What percent of the time does this yes receive a higher probability than the no's? Ah. And then how many times did we evaluate the yes to see how often the yes receives a higher probability than the no? There you go. And then we could test our knowledge right here to see if it works by going and adding in like another yes right here. And now we should get, so that's going to be, let's think right here for it. It's going to be 2, 6, right? It's going to be 2, 6 because we can, so it'll be that. And then that's 3. And so it should be 2, 6. And then let's remake the data or else it'll look like I'm wrong. But wait. What did it not like? Oh, because we don't have another probability. So we need another, they're wrong length vectors. And there it is right there. And we showed we can do it. So we showed the answer right there is this, and then we showed it this. So we calculated it mathematically. Yeah, that it orders them. That's the thing. Because you can have right here, this right here, this model is very, what is the accuracy of this model now? What is the accuracy of this model? These are perfect test questions, because if you know it, you know it. If you don't, you don't. What's the accuracy of this model? What is the accuracy of this model? Which you could argue two separate things. Someone could argue there's a way, a really nuanced person. Yeah, it's 1/5. This model is correct 1/5 of the time. But someone could argue, isn't it 4/5? Because you could just predict the, yeah, okay. If you want to be pedantic, you could argue that. But the model has an ROC of what? The model has an ROC of what? What is the, or AUC? When we run ROC, we'll get an AUC of what? Yep. Because the yes always receives a higher probability than the no class. At all points, the yes receives a higher probability than the no class. And we could probably make it a 50, and we could even do the drawing on this. If we do this now, it should go up, over, over, up. So if we do this drawing right here, we'll get up, over, over, up. I'm just going to throw that down. So if we do this drawing right here, this one that I just made now goes up, over, over, up, right? Did I miss one? It doesn't matter if it goes over twice. But it'll have a 50%. So up, over, over, up. Up, over, 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 up. Still the same. We run this right here. Don't worry about that number. It's a 50% ROC. And so these were the drawings I was trying to do yesterday, and my brain was just fading out for some reason. But this drawing right here should be over, 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 up. And the random chance curve is that right there. So, boom. Wrecked. Got it all. Got them all. So understanding what AUC and ROC is the most important thing. So you're supposed to email your lab 6, because my grade just updated 0 for lab 6. Did you email me it? Lab 6 was the one where you're supposed to say, Brian, I got 100. Brian, I got a 100. You can still email me. I'll let people email me until the end of tonight. And we are going to do a lab tomorrow. So email me by the end of tonight. Brian, I got 100 on lab 6. Do not forget. Email me. The zeros will be put in. If not, I think it must be updated last night. You did? Oh, you know what it might have been, Andrew? You might have started it. And then because of that, okay, just tell me to fix that, Andrew. Send me via email. What it might have been was you might have started it. Like I input the grade, but you started it. So when it closed, it put in a grade. Does that make sense? So because of that weird thing where it says you attempted it for like multiple days, what would that be? You attempted it for like a day and a half. So I think that's what it is like you opened it, and then when it closed out, it did that. So I think that's because I was like, I don't think I did that. I'm sorry, Andrew. I'm not trying to fail you, Andrew, I swear. I promise. I'm not trying to be mean. Okay. Let's continue on here. Let's just see a little bit. So no worries. I'm confused too. Cool. All this right here, false positives, false negatives, everything right here. Just all, once again, I don't care about kappa. It's compared to the random chance model. It's how much your model does in difference compared to the random chance model. And we look at how off the random chance model is from a perfect model. So it's the comparison of your model to a random chance model. And then we look at compared to what the random chance model had off of the accuracy. So, you know, it's a ratio of the remaining unexplained accuracy from the random chance model comparing your model to the random chance model. And so, you know, when you think about this, just think about it theoretically. Once again, kappa won't be on the test, but in case someone wants to know what kappa is, what we look at right here is you want your model to have very high accuracy. So if your model were to have high accuracy and the random chance model, which is like a random guess model, has lower accuracy, then you're going to see a big difference up top here. And then if there's like very little variation left to explain, then your model will do a lot better. So you do want a higher kappa, but don't worry, kappa's not on the test. No big deal right there. We might mention a few of these tomorrow. We'll do this. There's sensitivity and specificity. I will not put these on the test. Sensitivity is, in other words, the true positive rate, and specificity is the true negative rate. It's just memorization things. Here's the reason. Someone might say, Brian, why are these not on the test? I've always found that, tell me, and this is the end, well, class is over, so I can't go through any more slides. But here's my issue. I mean, one, these are not bad words to know. But we run into issues with, there's so many like specific words and statistics that sometimes you say a word to somebody and they just don't know what it means. And this is why we focus in on things like AUC. And we don't just say, AUC is this and we move on. We show it, we compute it, we think about it, we explain why we'd use it. Because if we want to put the yeses at the top, we'd optimize on AUC. If we want to be accurate in how often we make predictions, we'd optimize on accuracy. So we have two choices. Do we want to focus on being correct more, or do we want to focus on putting the probabilities towards the top, the higher probabilities of the yeses having a higher probability? If we want the yeses to have higher probabilities, we focus on AUC. If we want to focus on being more accurate in our predictions, which is what it is, we focus on accuracy. And most people understand accuracy. Accuracy is kind of like the baseline, what most people would think to optimize on, like, let's be accurate in our predictions. But then the kind of bigger way, the better way, in my opinion, is like, let's focus on giving the yeses the higher probabilities. And I never said AUC when I said that. I said, let's focus on giving the highest probabilities to the people who will purchase. I'm not saying AUC though. So when I explain this to somebody, I'd say, I want that if people are going to make purchases, we're going to give them high probabilities. I'm not going to tell them AUC, because if I say, oh, it's the area under the receiver operator curve, they'll be like, so we do know what true positives are. Those are things that are actually positive. We also know what a true negative is. That's what, let's get it right first. And we do know what a true negative thing. That's something that the fraction of individuals in the no class will actually know. So true positives are the things that are yes, that are actually yes. The percent of time we get a yes that is actually yes. A true no is things that are actually no, that are no, classified as no. And so I don't focus in on this too much, just because we won't use it too much. And I would rather just say something's a true positive. So since true positive means sensitivity, yeah, we'll do some off stars now. I'll probably do them later too. But this is why Brian doesn't go into much sensitivity specificity, because I'd rather just say true positive. And then I'd probably even have to explain to somebody what true positive means. So if you look, if I have to explain what true positive means to someone, I'm going to have to explain what sensitivity means to someone. So you say sensitivity, and they're like, what's sensitivity? You're like, it's true positives. And they're like, what's true positives? They're like, it's the percent of the yes class that are actually classified as yes. It's the percent of time we're right when something is yes and we classify it as yes. And then they're like, okay, wait a minute. So that's sensitivity. And also they sound so similar. So my problem with it has always been, you're explaining in business analytics, I don't see the utilization of it, because you have to explain to a business person a concept within a concept. And I don't like that. I never liked the utilization of that. I've always been against it. I think AUC is so powerful, though, and I think you can talk about AUC without. It's adding layers of confusion. Exactly. That's my whole point. We do have it in the notes here because it does exist, and it's not a bad thing to know, but I won't put it on the test because I don't think it's as, I mean, if someone's like, my teacher doesn't like sensitivity and specificity, it's like, yeah, I'm cool with true positives, true negatives. I mean, that's what those are. Yeah, the true positives, true negatives. Let's just call them that. Why do we got to have special words? I don't know. Why do we got to have AUC? Well, it literally is that. It's the mathematics. And that's probably why I like AUC better, is because AUC is what it says it is. The receiver operator curve comes from people, I think it was during the war, they were looking at birds and they were trying to figure out if something was a bird or not a bird. And they were looking at their sensitivity and specificity and all that good stuff on whether they could classify something as a bird or not a bird. And so you would want things that correctly identify the things that are not birds, the planes. And so you would want a really good receiver operator curve so that you identify the true positives, the things that are planes. That way you can steer away from the planes. So receiver operator curve comes from that. That was the receiver operator curve, and the area underneath it is basically being able to give the yeses the higher probabilities. So think about the bloop, bloop. It's a plane, it's a bird. No, it's Brian Facessi. You guys are awesome. What additional questions are there? I think, let me look at the next assignment for everyone here. Make sure we have covered all the material on it. Let me go into 474. Ask questions. Make some lunch. I've got to make some pasta because I opened some pasta sauce. I've got to do training. So much training. The grader looks to be getting caught up-ish. Vanilla and regularized logistic. Oh, you guys are fine. Let's do Friday. Look at that. We've already covered. Yeah. Let's do it. Let's talk about it. Vanilla and regularized logistic tree-based models and support vector machines. Cool. Oh, so we're not even gonna, yeah. I'll put support. So, yeah. I want to put, I think we'll be doing support vector machine. Let me think. I don't know. I don't think we'll get to support vector. Support vector's cool, but no rush. What's the thoughts in the chat? Do we need to get to support vector? Could you help me generalize the function in Q1F for homework 8? Yeah, of course. Let's do it. I have a quick question on assignment 7. I mean, the one due last night? Yeah. Yeah, and I know it's confusing because it says homework 9 on it. Here, we'll look at Anisha's question right here. What was it? What was the question on this, Anisha? And then we'll hop to Jordan's question. So we'll do the last night one, then we'll do Jordan's question here. Because Anisha said first too. So what was the question on it? You feel free to ask. Don't worry. We'll do that. It's a graph of question 3. I swear the questions are off. Overfitting. Yeah. Awesome. Perfect. Let's do the overfitting demo. Boom. Here we are. So, when we do this graphic right here, yeah, of course, definitely. So what's really awesome is Akaike's information criteria. Hirotugo Akaike. So Akaike was a very, very, very brilliant gentleman. He actually taught Humphreys Bosdogan. That's so cool. That's such a cool picture. Man, see, people make like fan art for him. I've met a lot of smart people in my life, and he just seems brilliant. Like I don't know. So this gentleman right here created this thing called Akaike's information criteria. You'd be like, well, cool, he made something. Akaike's information criteria is actually the 73rd most cited research paper of all time. Somehow I opened the stream and was streaming the stream. So sorry if you heard a reverb. That's why I like playing my stream through here. So we are still good, right? We're still broadcasting everything. So why this is so important right here? Why is Akaike's information criteria so important? Not just because, and why is everyone using it? Well, what it does, and so hypothesis testing, I mean, he did all this stuff right here, all this work, and there's the gentleman, Hirotugo Akaike. Hopefully I'm pronouncing his first name correctly. With all of this work he's done right here on it, he basically made a really good analysis for how our model is doing. And so this is a measure of how close our model is to the truth. And the question kind of states that. Now, what's going on with this graphic? We have here the training data, and we have here the holdout. Which of these is new data? The training or the holdout? Which of these is new data? Which of these is new data? Which of these would be new data? Which of those would be new data? New data is where? Which of those is the new data? Like, we're going to create our model from some data, and the new data is the holdout. The holdout is data our model's never seen. The training is the data the model learns from. So the model learns from the training. It creates its model from the training. And now we do validate it and pick it on the validation portion. Like we pick our model based on the validation. That's not in here. We're just kind of looking at the training, which is where our model is created from, and the holdout, which is where we test our model to see how it does on new data, which is our test of the model. And so what we generally see is that when we add variables to a model, our model will generally do water and water on the data it's created from. Here's the RMSE, or the error. So our model will generally do water as we add more variables. As we add more variables, our model generally does water on the data it's created from. On the data our model is created from, the model will generally do better. It'll have a lower error. So you can see the relative error, which is measured in RMSE right here, going down. And this is on the data it's created from. But you'll notice on new data, it goes down, and then it starts to go up. And the idea of overfitting is a model that works really well on the data it's created from, but works really bad on new data. It does not generalize to new data. So when does overfitting begin? Right here. This is where we see the first impact of overfitting because it does the best here. If you kind of smooth this out, it would kind of smooth out to having a bevy right here. This is where the overfitting kind of begins. I mean, someone could be pedantic and maybe say 6. It's somewhere, if we were to be like, overfitting occurs in this area. This is where the model works really well in the holdout. It starts to work worse as we add new variables. This is the perfect symptom of overfitting. A model that works worse on new data than we would have expected it to work. Like it works really well on the data it was created from. And so I equate this to, imagine you ask your friends that you're going to say, I'm going to make pizza for you. So you're going to say, we're going to make pizza. And you go to your friends and you say, I'm either going to take 4 bits of advice from my friends or I'm going to take 20 bits of advice. So you're going to ask your friends for 2 bits of advice on making the pizza, and they could be like, oh, you need to put cheese on it, like extra cheese. That's my 1 bit of advice. Or yeah, 4 bits of advice. So extra cheese, pepperoni, bake it for 30 minutes, and this. Now you're probably going to get some pretty standard advice that if you went to new friends, they'd probably like the pizza about the same. Now technically this is the original friends and this is the new friends. But if you were to get 20 bits of advice from your friends, you would probably what that to the friends you make the pizza for. You would probably, if you got like 20 bits of advice from your friends on how to make the pizza, you'd probably what that to the friends you're making the pizza for. You'd probably what that to the friends you're making the pizza for. For the original ones you get the advice from the ones you learn from. You notice how this is the training data? This is the ones we're learning from. So we're going to ask these friends for 20 bits of advice, and we're going to what to these friends taste now. Think of a stat word. We're going to like blank the model to these friends taste. We're going to predict, well, we're going to make a model that explains, we're going to say, okay, they're going to tell us use this, use this, use this, use this. They're going to tell us 20 things. So our model might be what to those friends now, because then we're going to try it on new data, but it might be what to the original data. So we're going to see if it generalizes, but it might be overfit to the original friends. So over here, we might overfit to the original friends, and 100 office hour points right there to Andrew and Vedrina. So, and then it does not generalize to the new friends. Does that make sense, Anisha? That we have here that we overfit to the friends because we took so much information from the original friends. We now have a low bias, high variance model. So we're trying to find this happy point right here that has, I mean, this isn't the lowest bias, but it's doing well on new data, which means it's probably got low variance. So it's like medium bias. I mean, the best point might be in here where we have like lower bias, but some variance. Like when do we see overfitting? We see it right here at 5. Where might be the best model? It might be in here somewhere where we have a lower bias, but we are seeing some variance where the model is doing worse on new data. But does that make more sense that this is kind of showing the variance and this is showing the decrease in bias? AKE's information criteria does have a correction for the number of predictors in the model. So it is going up here at the end because it does correct for number of predictors. So it has a penalty term for number of predictors. That's why it doesn't always go down. It generally goes down though. Awesome. Yeah. So if you might be like, well, this, don't worry, because feel like, well, this is going up. It's like, okay, he corrected for that. Brilliant man. So thank you, Dr. Akayike, for your contributions. Lived a good life, lived to like 90 or so, and taught Humphreys Bosdogan. And now I've been taught by Humphreys Bosdogan now. Those are tough classes. I did those tough classes. Oh man, PhD classes. Those are fun. They're fun. No more for me for now. Which one was Jordan looking at? Q1F. Let's look at Q1F right here. Q1F. Modify your code that it works inside the function pairwise AUC. Remember that the 2 arguments will be the vectors of actual and predicted. You can assume that the actual will always be contained the yes, no, and the predicted. So we're making a function right here to do the AUC. Test your function with the vectors scores for individuals and actual class scores defined by the code below, probabilities. So here I might just do this from scratch right here. And so you have to make the pairwise function. And do I have the environment loaded? This computer probably doesn't. Yeah, I didn't think it would. Oh, wait. So we should, wait a minute. Scores for individuals. Where's the scores for individuals coming from? Scores for individuals. Set seed. Here we go right here. Actual and predicted. Cool. So we should get some actuals and we should get some predicteds right here. So here's the actuals. Here's the predicteds. Cool. So we have our actual, we had our predicted, and we need to make an AUC function. So this is going to kind of walk you through this whole thing right here on making a data frame. So make a data frame called values, whose first column contains the actual, whose second column contains the predicted, and we should include the results head right there. So I got this. Yes, thank you, Jordan. 1,000 off stars points. Make sure to do that. Oh, because you're getting, I bet you our results are different, right? Jordan, thank you so much. Because I bet you're saying, Brian, you're about to get a different result than me. Yes, I'll try to send out a reminder. I might have had it set to that. Yeah, so it looks like I had it set to that. Sorry, it's super confusing. It's like if you don't have the right RNG kind, you get different values. How do we make a data frame? Data frame? Oh, it wants to call it values. I always call it data frame. Yeah. Put it in chat, you bet. Thank you, Andrew. There you go. Always feel free to ask. That's why we hang out, do some office hours. So we can alt that. Okay, well, it should do this. And that should do it. What? Oh. There we go. So we are good right now. We are good. Make 2 new data frames. A yes and a no, which contain the rows corresponding to the yes class, which contains the rows. So these are the actual and the, okay, cool. So now what we want to do is we want to subset this. We want to go to subset values, and we want to do actual equals yes, and that's got that. And then we want to go and we want to subset and go here and go no. It's capital no. And we want to do this. Now, here's the thing you should always do is you should always take a look. That's why it's got the checks. We look to be good on the yeses. We can do the sanity check and we should be fine. That's good. And you can leave sanity checks in if you want. Please tell me if the grader takes off, but we have this right here. Remember, slow it down if you want, but this is just subsetting right here. And I like to divide my code up. We could have done, there's only one condition, but we're just saying subset the values where the actual is equal to yes, and make sure to do your double equals because you're doing is it logically equals because we're setting a condition. And then we're storing this subset into yes. What are we building right here? We're building the skeleton. So we'd like to practice building our functions. So consider the score in the second row of yes is this. By taking the mean of a logical condition, find the fraction of no scores that are smaller than this score. Cool. So we need to go to the yes vector position 2, and what we should do is we should go to the predicted. Cool. We have now pulled this number out, and now we need to figure out the percent that are what. I need help for this, which actually it's a lot easier than you think. What should I finish off to write this one out? I need help. I'm stuck. I don't know. I got this far. I need to figure out the percent of things in the scores that are smaller than this. So I need to figure out, so that means it could be bigger than it. I need to figure out the percent of no's that are smaller than this. Yep. And that's right. Andrew's got it. I mean, yep, Jordan, sorry. Can't even think today. No $ predicted. And then this right here. And then we're going to take the mean of that vector. Always run your code after you do it to see if you get what you want. And that's the answer. We could also check the no vector just to see if the third value is smaller than it. And it is. So this confirms why we got the true right here, because it was bigger than this one. So always kind of like look to see if your code's doing what you want it to do. Be like, okay, wait a minute. This returned a true, so this has to be bigger than this. And so now we've checked this one. If you can't tell, now we're going to go through, and I can kind of tell you where the rest of this is going because we're almost there. Now write a for loop that does this for each of the yeses. Okay, so we need this. We're going to go here 4. And we're going to go here, and it needs to do it for each one of those. That's what's going to change. This is going to be I, and then we need to go here through I, and we're going to, for 1 through the number of rows in the yeses because it has to do it for each yes. If you think about what n row of yeses is, it's going to do it for every single observation right there, and it'll change what the observation is. And then we probably need to store this into an object right here. And so this will be stored into a position, which will have to be created right there. That'll just create the thing for us to store into. And then whatever this is, which we can just call this PC, and we could store into, we could do it on one line, but I like to break apart my lines sometimes to be like, okay, now we create it, now we store it. I mean, you could literally, why not? Sounds like why. So you can just do that right there. And that should do it. Hopefully. Always take a look at what you create. We do see right here, this is the one we ran previously. So we do achieve this value right here. We should also see that the third one in the yes vector, whatever is in yes, should be higher than all of them. And the third one is 96, which if we go to our nose, 96.28 should be higher than every one of these, and it is. So once again, what am I checking? I'm making my own sanity checks. Does that make sense, Jordan? That when I saw here that on this one, this one equates to this one that ran, it was higher 100% of the time than all the no's. And I look and I'm like, yeah, 96 is higher 100% of the time. So do your own sanity checks. Be like, what is this doing? Is the code evaluating what it should evaluate? And like 86 is higher than, because there's 8 of these, I believe. 1, 2, 3, 4, 5, 6, 8. So 80, oops, it's 86.63. Oh, and this is the one it's not higher than. Oh, interesting. So the first one right here was not higher than this. It's higher than 7 out of 8 of those. So we've confirmed this. Left arrow into the AUC, the average of these values. So cool. So we just do the average. So mean of P. There we go. And there's the AUC. We did it. That's the AUC. And oh, so that would go down here. That's the AUC. Modify your code so that it works inside a function of pairwise AUC. So remember that the two arguments will be the vectors, the actual, and the predicted. Okay, cool. So this is where it gets fun. Let's remove this. And sure, you can go away for the moment. And we're going to, I'm going to do this. Be careful doing that. I've just destroyed the chunk. This chunk down here is completely broken. I'm going to fix it up here in a moment. I just kind of want to, like I do this so that it ends the chunk, but I can be careful. What I'm doing here, do not do that unless you know exactly what that does. You can destroy your whole knitted. I mean, email me if it doesn't knit, but I do this so that it ends the chunk, but that'll cause problems for the remainder of the document. This is broken right now because of what I did. So if you know, if I remove this and I go down to here, that's no longer broken. But once again, please be careful doing something like that. I've had people do that when I'm showing how to do things. I do it so that when I run this, it doesn't go all the way to the bottom of the code. That's why I do that. What I'm doing now is I'm going through everything I've created. This was here me just looking at it. No, that's the answer. So that'll be our return. Oops, be careful. We don't want that there. That's going to be what we return. What was that correct? Is that what we return? Yeah, I think so. We're going to re-indent everything. That's where we make that. That's good. Did we take the mean? There's the mean, yeah. Okay, so we did that twice. Okay. Yeah, we did up there. No, we did lower. That's like, why is it there? We don't need that. I think we're good. Oh, we need the subsets. We need the subsets because we'll have to subset it inside of here. We'll just kind of move it over to there. So there's our subsetting of it. And I think, and then we have to turn it into a data frame because the first thing we did was make it a data frame. So we made it a data frame and we have the actual and the predicted. Okay, cool. So there's only two arguments right here are the actual and the predicted. It should say the actual and the predicted. So actual and predicted, yeah, cool. So someone will only have to put in their actual and their predicted. There's that. We'll kind of make this its own thing. We could put a comment right here. We could say makes data frame. And then we could put these two side by side and go right here and say subsets the yeses. Would it be, sure, grammar? I don't know. And then this right here, whoops, what did I do? Don't do that. And that subsets the no's. This right here runs all pairwise or creates empty vector. This right here runs for loop. checking if each y is properly ranked. And this figures out on average percent y is properly ranked. So if you can't tell, literally this has been the AUC thing we've been talking about. And one thing we need to do now is we need to go to return and go here, and we need to return that. So make sure you have the things where they need to be. So that is our function. Looks good. We're just going to clean it up a little bit more by doing the following. And there's the end of our function. Remove that. And then we're going to bring this right here. I like this is just how I clean functions. We're going to go to code, re-indent lines, just make it look a little more better there. We can delete the spaces between them. And I think we are good. And we just wrote like a good 11 lines of function right here. We run this. We hope it works. We go, see, that's why I did that. Got library red class, library caret. We got the wine data set. We got this. We run that. Run this, run this, run this. And is that what it wants us to get? Hopefully it does. And it's getting a different number. No. Are you getting different numbers? The take home will be due Wednesday too. The take home will be due Wednesday. Let me see what's happening with our different numbers right here. Don't like C. AUC estimate of RSU uses a slightly different procedure. Cool. Yeah, cool. That's what I thought. I was like, I remember it being a little bit different. It uses a slightly different procedure, but that's fine. So we are good. We are good to go. But it's estimated by the ROC. So it uses, but we were doing this also earlier. So I do dislike that it does like, it says not found. You might need to send me it. You might need to send me it, Jordan. You might need to send me it. You might need to send me it. It's basically, you got it now? Awesome. And that should be right here. I think that's got it. That was a really good big question right there. But just following through the steps, going through each part of this, just being exact and making sure not to make errors. It's just, yeah, and there's GLM net grids. We're good on that. I should send it out probably this weekend. So this weekend, I'm gonna hopefully, I might be able to send it out tomorrow night. My gosh, it's already Thursday. Just mini term happened. You know, it's everything's just a blur right now. Everything's just a blur. Did you get setting levels, control equals no, and case equals yes, same direction controls? Explain, Jordan. Sorry, my brain's not processing exactly what you mean by that. Was there an error? Oh, yeah, you're right here. Setting levels, control equals no, case equals yes, setting directions, control less than case. Yeah, I think it's just setting the, yeah, it's a warning you got. Yeah, it's just a warning. And you could suppress those warnings. And so, yeah, it's just saying to you like, hey, here's what we're doing to your levels with the, we could look at the actual cases and stuff like that. Can you run code down here like that? No, you can't. Looks like no. Actual cases. There goes that. And scores. Yeah. Pairwise AUCs. And ROCs. And pairwise AUC. Yeah, and that's our function, the pairwise AUC right there. That's got it. Nice job. Good job, Jordan. Excellent work on this. And we'll do tree-based models, and we'll have a little bit of theory on support vector machine on the test, and neural nets we won't really cover. I mean, we've got the notes on it. I can always tell you more about neural nets. The notes are very short on it. We've included it on the test. I'll see if I include neural nets. If I do, it'll be very simple neural net stuff. I'm thinking I might just not include it. I think we'll get to support vector machine, and I'll tell you a little bit about support vector. We've got basically 3 more full days of class, and on Wednesday I might mention stuff, but not really go in depth. Like Wednesday is just going to be me sprinkling stuff on, but there won't be deep topics. Like with neural nets, the biggest thing you would need to know about a neural net is literally making weighted models. So a neural net, it's so cool how a neural net works. I mean, it's just one of the coolest things. Like people are like, how does a neural net work? It's like, oh, it's so beautiful. Neural nets. Let's take a look at one real quick right here and see how a neural net works. I'm going to pull up the neural net notes. It's just the things people have thought about when you realize the things we're capable of doing. There's neural nets and deep learning. Oops, wrong button. The things we can do with neural nets are absolutely brilliant. Someone's going to be like, oh no, when did he start teaching this? So let's hop back right here real quick. If you notice, there's only 26 slides on this. It literally is the icing on the cake. It all starts with this perceptron right here, which I want you to think about this. This is x sub 0. This does not have an x variable on it because it's x sub 0 and x sub 0 equals 1. Do you know what this basically is in regression right here? Just think about this. What is this? I know it's not. I like that. I like that. It's not exclusive because we might. I don't know how much of this. I don't know. I don't think we'll put this on the test. I just don't want to rush anything. I'm not about rushing through material. Yesterday I was not as productive, but it happens. Everyone's allowed one off day. I got my one off day. I'm gonna stop talking about it. Think about this. This right here is equal to 1, and then it has a value. Think about just regular old regression. You have your x, you have your beta 1. You have your x2, your beta 2. Your x to another variable, this right here. This term right here is the what in just good old regression. This term right here is a what in good old regression. You've got your x's that control the coefficients, and you've got one that is like an offset. It's called an offset here. But this right here, when you look down at it, is basically the what of a regression model, because these have x's. Who knows? Office hours exclusive, 1,000 points. This thing right here is your what in just when you think about regression. It's just the what of a regression model. That's what it is, Jordan. It's just the intercept. We're going to call it an offset here. So it's technically called an offset. I mean, I said it a moment ago, but that's what I wanted you to say. I wanted you to say intercept. It's just the intercept. That's all it is, which is an offset now if we talk about it here. This model is going to predict a yes or no. Vajrana, 1,000 points also. Yep. And this model predicts a yes or no. So it's kind of like a logistic model, but it doesn't have the logistic curve to it. We can make it a logistic curve if we want. I think we show that right here. So we can fit a logistic curve where it does the probability. So all of a sudden, literally everything we were talking about today, this is the logistic curve. And this is a singular perceptron. This might as well just be a logistic regression. That's all this might as well be, logistic regression. It's everything we were doing today. We've already covered a third of this lecture, basically. And it's like, wait, this is just logistic regression, just differently. But you know what we're going to do with these perceptrons? We're going to take and not have one perceptron. We're going to have a bunch of perceptrons. So now you have your x's right here, because here's all your x's. And then your x's go through here, and this is like the perceptron they're going through. So if you're wondering what's happening, the thing you saw back here, right back here, here's your x's. So here's the x's, and then here's them going into a model, and then you get the output. Here's your x's, and here's the one perceptron it's going through, and then you would get the output. But guess what? Instead of just using one perceptron, why not use a bunch of perceptrons? Now we have 4 perceptrons, and the perceptrons will work together to make a model of their own. So the perceptrons, you have like just a singular perceptron where we have your x's, which is your variables that you're using, you're collecting on, like height, weight, GPA to predict something. And then they go and they make a model to predict it. But then you use your models. Your models are used to make a final model. Does that make sense what's going on here? That instead of a singular perceptron, just one of these, it's like a brain, like a network in a brain working together and solving a bunch of things, and all these like neurons firing. And all the neurons are firing to figure out. So you make a model, but then your models come together to make another model. Who thinks they kind of get what's going on right here? It's like you make a model, and you make another model, and you make another model, and then your models all come together to make another model. So you're making models that make models from models. Your models are made from models. It's neural nets are awesome. Does it make any sense to anybody right there? That instead of like making one model right here, because this one perceptron right here is exemplified right here. There's the one perceptron. That's the one perceptron. The models become, yes, Vajrana, that's worth 1,000 right there. The models become the variables in the models become the variables in this model. Does that make sense? The models are now weights within another model. The models become part of another model and become the variables of a final model. We don't really look at this inner part right here because we're not going to like evaluate the models that make the model. We want to look at the final model. And so the models make models, which is just, whoa. But you know what's even crazier? Why not have X's that make models, and then your models make more models, and your models make more models, and then you get your predictions here at the end. And you don't even have to predict a yes or no. You can predict things like a button press on a controller. But this is what we mean by deep learning. Deep learning is when you have more hidden layers, more models making models inside of models. So your models, you start off by collecting your X's, and then you make a model from them, like a singular model. Well, why not make a bunch of models? And then these models come together to make more models. And these come together to make more models, which make your final prediction. So when you think about it, it's models making models making models. The deeper the learning, the more models you're making, and the more hidden layers you have. The hidden layers are the models making models. It's insanity. And people thought, it's Rosenblatt is the guy's name. He's got a fun name to say, Rosenblatt. Where's his name? Rosenblatt. Frank Rosenblatt. Frank Rosenblatt is the guy who made this up in 1958. And he was like, cool stuff, but we don't really got the computing power for this. This was invented in 1958. And it's one of our most modern techniques. And it's based on his perceptron work, which then created models on top of models on top of models on top of models. And aside, you basically know the whole, and how do we use it a lot of times? It's used a lot of times in like image recognition because you can break down the parts. Picture recognition is huge for it. So it can very quickly identify what's going on right here by the features of something. It's just so good at image recognition. Neural nets, that's why, self-driving cars use neural nets. Here's the tuning parameters for it. We can tune the number of hidden layers, the number of neurons, the weighted decay, which is the regularization, which is going to control the bias variance trade-off. As soon as you see weighted decay, like here's a fair test question I could put on the test. I could say weighted decay is how we control for regularization in neural nets. What is this controlling for? RMSE, AUC, bias variance trade-off. So weighted decay is how we control for regularization. What is this controlling for? AUC, RMSE, bias variance trade-off. So regularization, technically it's controlling the variance of the model. Like the regularization is the variance of the bias variance trade-off. So, and the other ones, the AUC and the RMSE are measures of bias of a model. Yeah, it's gonna be bias variance trade-off. Just the keyword right here, regularization. Anytime you see that, it's bias variance trade-off. Like that's instantaneously, we should know that by now. We talked about regularized regression, regularized logistic. So the weight decay is that. Number of hidden layers is literally controlling, it's controlling this right here. That's what the number of hidden layers is controlling, and the number of neurons in each hidden layer is controlling how big this is. So think about this. What you're literally controlling for is how many hidden layers you want and how many neurons you want. So you can try deeper learning by increasing the number of hidden layers, and also increasing the number of neurons will make it work longer on it, which could be good. I mean, you would think. I mean, it's going to make it do more work. Computer can handle it, hopefully. And when you look at it right here, I think we have, here we go. And this is about the hardest test question we can write. We've literally covered all the notes. Just being able to write out the equation. If you notice here, here's the intercept. It's very hard to see this probably, but you would literally just take the intercept. If you wrote out the equation for the top neuron right here, which is going to be this one, it'd be the intercept. See, there's the intercept, negative 14.8, and then you would times that by Bill. Here, I'll try to get on screen where you see it. But I'm not going to put a question like this on the test. What exactly do we need to put for 2A? Let's hop back to that. But this is the hardest questions we can write on neural nets, at least with what we teach you. And of course, you can run them in R. Like literally, here's the code to get the predictions and to run them and the pros and cons. Yeah. It's only 26 slides. It's really meant to be the icing on the class, and I do like talking about neural nets because they're so cool. Neural nets are cool. But, you know, we don't want to rush through material. We just taught all of neural nets. Let's hop over to those screen. What exactly do we need to put as a response for 2A? What does 2A say? To be on the safe side, Weller threw everything under the sun into the dataset. This is a double-edged sword. Many columns are near duplicates of each other. Dun, dun, dun. Or linear combinations. No. Means redundant information. If those three columns exist in the data, and it might be the case that some columns have very low information density, which means they have very low variance, near zero or zero variance. To discuss the presence of absence of these issues. Follow the examples in the activity. Note the later two of these functions only work for numeric columns. I've included a command that creates a vector of column positions to help you out. Okay, so let's take a look right here. We've got the data right here being read in. I'm not in my working directory. Set working directory, choose working directory. Downloads. And let's go right here. Really? Did I not download that just a moment ago? It says wins parentheses. Computer, what do you do? Really? Where did that download to? It's in downloads. Let's call it this. Wins. It's in stat tool 1. Wins, copy. Wait. Wins. Am I going crazy? Error, no found. Session. Set working directory. Choose working directory. Documents. Well, that's why. Downloads. Open. Go too quickly there. Read 32 items. Good. So we added that in there. And yeah. Okay, cool. Let's take a look at what's going on right here. The info density right here. So we're seeing, oof, wait, something's wrong. Something's going on. Near zero variance. Okay, good. Oh my gosh, that's so much. Oh, let's take a look right here, Jordan. Let's take a look. Yeah, so what we're looking for is kind of the junk variables. And it looks like we don't have any zero variance or near zero variance. So this is something we talked about a while ago in one of the activities. If you remember, we went through and we looked at near zero or zero variance. Was it Monday? So if you're watching this right now, I think it was Monday we went through and talked about this. And we should get, and the reason it's giving this right here is I think there's no near zero variance. So this is coming back with there's no near zero variance. So why does this turn out like this? There's nothing to report. All of these NAs right here mean there's nothing because we don't have any positions where there was near zero variance. Does that make sense right here? What does near zero variance mean? Like, what is this looking for? It's looking for variables in the data frame that have what? Either one of two things. We're looking for data that has what or what? Because this is step 1. If you remember, we talked about step 1 is to get your data ready to go and to make it look all nice and good. And so what is going on right here? These are trying to see if the data has what or what. What it would be if it has zero variance or near zero variance, which we could, watch this. I bet you, I think that takes a data frame. Watch this. Let's make something that has near zero variance. Data.frame, we kind of did this before. Let's go here and go 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. We could have just done rep. Probably would have been better. Sure, let's just do that for now. It's easier to see what it is then. And then we're going to go here, and we're going to do this, and then we're going to go to 0.1, and then we're going to go here, and we're going to do this, and we're going to do 10, 20, 40, 80, 90. Okay, cool. That should. Good. And this. Okay. So now let's take a look at what we got right here. Okay. Oh, that didn't give near zero variance? Really? Let's try that. Really? Gotta be kidding me. Oh, wait. Near zero variance. I'm shocked that that does not. Let me clear the bottom output. Info density. All B. How does that not have near zero variance? Let me try to make something with near zero variance. Because I thought that would have near zero variance. Huh. Must not be enough. Let me try one more time because I'm shocked that does have near zero variance. Rep 0 999 times 0. Rep, and we'll call this like 0 var equals that. So that's our one with zero variance. We're repping 0 and we need to concatenate now. Okay. So we're repping 0. Does that make sense what I've coded right here, Jordan? Is I've repped 0 1,000 times. That's zero variance. That's what zero variance means. So that'll have zero variance. So that's our zero variance right here. And then we're going to go here. We're going to take this same code and we're going to go to the next vector and we're going to try to make a near 0. So this is going to be near 0. So this is near 0 variance now. And this near 0, 1 is we're going to do the same repping here, if I could type. And then we're going to put in a 0.1 at the end. So this doesn't have zero variance anymore because it actually has variation in the data, but it has near 0. Then we're going to put in like variation. So the variation one is just going to be random normal numbers, and we're going to do 1,000 of them. So this just creates a vector of 1,000 random normal numbers. So if I am correct, and I really want to see that that second one is reported to have near 0 variation. There we go. That's it right there. That's what I wanted it to report. That's exactly what I wanted it to report. I just think my sample size wasn't big enough the first time I ran it. So when you look at the way this is reporting it right here, you don't have to look at the frequency ratio, the percent unique ratio. I mean, that's gonna, yeah. So the way in which it decides what is zero variance and near zero variance is based on these metrics. And this one was decided to be zero variance because everything is the same. And so I was able to achieve that last time. And then this one was decided to be near zero variance because it does have something that's different. And that's the reason this is near zero variance. Does that make perfect sense right here? That really the first and the second variable do not give any information. They're x's that don't contain info. The first one especially. The first one has no ability to explain. It's a junk variable. It's complete junk. It's a waste. This is like work smarter, not harder. If you include that first variable in your analysis, you're just having your computer do work it shouldn't do because it won't do anything. It doesn't. It's useless. It's completely and utterly useless. If you include the second one, I mean, maybe, especially for maybe trees, that's where we get into debates. No one can debate and say include the first variable. The second one is where you have debate, and the third one is it's actually a perfect variable because if you look at it, it's just randomly normally distributed data. I mean, it's not good that it's random. Hopefully it has a relationship to your y variable, but that right there would not, that's what we want. We want variables that have variation. We want them to be normally distributed. So this right here, once again, would be a very excellent variable, not because it's random, but because it follows a normal like that. If you can't see it, boop, there it is right there. Now, if it is randomly distributed, or if it's not distributed, if it has a random relationship to our y, that would be bad because then everything we would see related to it would be by random chance. But hopefully it has a real relationship. I did create them randomly, but hopefully it has a real relationship. I'm going down to here. So don't put those things I put in. That's just examples. We're doing the EX3. Okay. So now we're looking at the info density here. The reason this comes back with nothing when you run this is because there was no variables with near 0 or 0 variance. You could also check this by going to here to not running the 1 through 5, and it's going to report nothing. There's nothing. We didn't find any variables with 0 variance or near 0 variance. If you look at this code right here, we're going to apply. So since there's no positions with near 0 variance, it means that it means that all columns in the data frame have variation that could be useful in explaining the y. Since nothing was found to have 0 variance or near 0 variance, all the variables in the data set could be useful in explaining the y variable because they have variation. And what do? We use the variation in x to explain the variation in y. So it's possible that we could utilize the information in these x's to explain the y. Does that make sense, Jordan? Like, it seems reasonable to believe that we could investigate the relationship between the x's and the y's because the x has variation in it. If it came back as 0 variance and the x has no variation in it, it's completely useless for explaining y. If it came back as near 0 variance, then the x would have next to no ability to explain the y. So 0 variance, no ability to explain y. Near 0 variance, next to no ability to explain y. And what is near 0 variance? Well, I mean, that's where we get into like, well, this has little variance, has like a lot of variance, and then you want the variation to be normally distributed. So good job, Jordan. Excellent work right here. Numerics, so we look right here. We're going to look right here, and we're going to figure out if things have classes contained within this. Let's go ahead and see where are our numeric columns. So the only thing this code is doing right here is identifying numeric columns. If you look at the lapply right here, we're just going and we're finding which things are contained within the vector numeric integer, which turns back trues and falses. The very end of this vector should be true, true, bunch of trues, unless there's multiple columns after 137s, but there's all the trues. And if you see the falses right here, we do not get these positions, which look to be 33, 32, 31, 30, 29, and 28. So you won't see 30, 29, 28. There we go. There's where you're missing 30, 29, 28 between those. And we don't get that because this is wrapped inside of a which. So these are the positions of the numeric columns. Now, why are we getting the positions of the numeric columns? Because when we do this find correlations right here, we are going to see the correlations right here of only the numeric columns. Notice how this is the row space and this is the column space. We're only going to get the highly correlated, so we're going to take the correlations of this, and then we're only going to report back the correlations that are at least this. And so here's the combinations of the highly correlated, and there we go right there, 15, 18. And this is how many are highly correlated. There are 35 highly correlated variables. So something going on right there, 35 highly correlated variables, interesting. So there is an issue with things like variable 15, 18, 21, 23, but 35 of our, was it 137 variables? 35 of our 137 variables have highly correlated relationships with other variables. So that's the interpretation of what this code is telling us. 35 of our 137 variables have highly correlated relationships with the other variables. Linear combos is going to tell us if one variable is a literal combo of another variable, which would also mean that that variable is completely useless to us. Let's take a look here. Linear combos, boom. And it'd be very interesting to see what these are. Let's go here to, we don't do that yet. Let's see what these variables are. Oh, wait, there we go. Linear combos. Ooh, oh, this is such a cool code. 2, 7, 8, 9. So 12, 7, 8, 9. And so we should be able to go combo info list 1. No. Oh, position 1. Okay, there we go. That's the first linear combo right there. And let's go to EX4, EX3, NFL. Let's go to the columns there. Will that not return? Oh, is that not a vector? Can we do that as dot vector? Oops, wrong button. Okay, that. Let's go to unlist. Cool. I just want to take a look at what's going on. There we go. Let's go to names. Let's just look at what their names are. Okay. So these are apparently linear. There's a linear combination that exists. Fumbles lost, total offensive yards per play, offensive total first downs, and offensive pass first downs. So that's a linear combination right here. Offensive pass total, rush, offensive total, turnovers. So this right here is saying that these are linear combinations of each other. Offensive pass, offensive rush, offensive turnover. And I think there must be a total on here. Let me look at the names of. Let me see here. Yeah. So those are the ones, offensive total pass, offensive, so 13, 6, and 7. 13, 6, and 7. See, there's first downs. Yeah. So it's these are where the linear combinations are coming from. So you can go to combo info, and it wants to remove these right here. So these are the ones it's suggesting we remove, and we could go here to, is that the third list inside of here? Which item is that? That's item 1, 2, 3, and that's the remove. So we can take that vector, and let's go here and look at those. So let's go to the names of the EX, and we already got that right here. Which one is it suggesting to remove? We want it in the column space. It's suggesting we remove fumbles lost, pass touchdowns, offensive game winning drives, blocked, kicked, or missed. Because what it is, and to make sense why it's telling this right here. So Jordan, here's the big thing on this. These are the columns it's suggesting we remove because, and here it is right here. Here's where we're removing the stuff. If you take a look right here, it should be the removal. There's the minus the which, the names. There was all that good stuff right there. What we're going to do now is we're going to remove out, this is step 1 of the work. We're going to remove out the things that are just going to kind of clutter up the computer, that are going to make it do extra work it shouldn't do. Because if something is a linear combination, of another variable, it cannot possibly bring what to our model. If something is a linear combination, and I can show it right here, we'll use the find linear combos code, and we can just do it on a data set. It cannot, exactly, you get it. And so we can run this sort of thing on a different data set. So let's do combo info, and let's do the following. We're going to do a data frame. Well, we need to do, right. So we're going to make a new data frame here to show how this works. And data.frame, and let's do x1. And x1 is going to equal the 1, 1, 1, 1, 1. Sure, let's just do 5 numbers. I'll make my life easy. That is that. Okay. And then x2 is going to equal, and I think it might find, we'll see if it finds that. This is, well, it has no variation too. And then let's go ahead and do x3 equals 2. And you can see that's obviously a linear combination of the first two. The first two don't even bring any variation. Then let's do x4 is going to be 5, 1, sure, 1, 5, 1. But then x5, did I put a comma? Didn't put a comma. x5 is going to be 6, 2, 2, 6. X5 is a linear combination of what? X5 is a linear combination of what ones of these? X5 is a linear combination of what? So you can see here X5 is going to be a linear combination of certain ones inside of this data frame. Yep, there's going to be a linear combination of this, and what else? So we can run this right here. And it'll be X5 is a linear combination of X4, and then technically, because like matrix algebra, technically it's any of the other ones. And so I just ran that code, I believe. Yeah, here we go right here. And so if you look right here, the linear combos, it's saying that 1 and 2, 3 and 1, and then 5, 1, 4. Yeah, and there's the 5. Here's the 5, 5, 1, 4. And the 1 and 2 are combinations. They're mathematical. And I'm surprised it didn't do 2 and 3. So what is this suggesting to remove to us? It's suggesting this and these. And look at what it wants us to remove. Does it make sense that if you remove this and this, that you don't lose any of the variation? The ones it's saying for us to remove are this. This does not give us new info because it's just x1. And it's saying to remove this because this does not give us any info. It's just a combination of 1 and 4. Like x5 right here is a combination of 1 and 4. So it's kind of saying 2 is a combination of 1. How is 2 a combination of 1? It's just times it by 2. How is 3 a combination of 1? Just times it by 3. How is 5 a combination of 1 and 4? Well, you just add 1 and 4. And it can get more complicated because if we were to change this to something like this right here, we should still get the same result. If you were to change this, because you'd be like, well, wait a minute, how is it working now? We should still get the exact same result right here. We should still get that 2, 3, 4, 5 to remove, yeah. Reason being is that it goes back to matrix algebra. 5 is still a linear combination of 1 and 4 because X5 is, you could literally show it right here. You could say, well, data frame $sign X1 times 0.5 plus data frame $sign X4, and then you get that, and then you could check it to see if it is. I could do, and then data frame $sign, and then you could see if it's identical. I think identical should do this. Yeah, and they're identical. So this confirms that these two vectors are complete linear combinations of each other, and we could print them to show them by doing this, but the code identical just sees if they're identical. And so this right here is a linear combination, and this is what we're checking for because we want the variables to bring new information. So just investigating, and it's just good to practice and kind of think of what these codes are doing and why they're doing it, and the more you kind of write code. But Jordan, that's got it. It's a really good kind of start to like a little bit of early afternoon office hours. Is it making more sense, Jordan, like why we do these things, like why we don't want to put in variables that bring no new variation, variables that are just combinations that are just kind of like going to clutter up the model. So we're like, oh, we don't need to waste the computer's time with this. We want to give it new variables that bring with it new information that help explain what's going on. Yep. And so that's the whole point, is that this X5 is useless. The only important information right here are these variables. And truthfully, the only important variable in this data frame is what? Ooh, this is a good test question right now. Ooh, it's a tough one though. What is the only important variable in this data frame? I mean, but you could kind of guess it. You could look at it. It'd be between two of them. What is the only... There's two answers too. There's two answers. There's only two answers to this question. Yeah, it's X4 or X5. Those are the only two answers to the question. Because these have zero variance, so they're not important. They don't bring information because they're just 0, 0, 0, 0. It doesn't matter. It doesn't matter if it's 0, 1, or 2, 3. If it's the same number repeating, that doesn't give any information. It's no information. And then right here, these, like you could make X4 from X1, X5. So you could say X4 is a linear combination of X5, X1, but X4 and X5 are... they're intertwined to these other ones. So yeah, that's got it. That's a great job. Awesome job. It's either 4 or 5 has the important information. See, now that becomes a good question. If you could only keep, what are the two variables that you might consider keeping this data set? Either X4 or X5, X1 or X4, X1 or X5, X2 or X3. And probably people would say keep X1 and X4. That would be the trick, because people would be like, wait, X1 is different and X4 is different. But you also have to think that X1 through X3 have zero variance. So you would keep them because they have zero variance. They're not important. So it's a good, tricky test question. I don't know. I just try to think of questions. I'm not trying to make, I feel bad because I'm like, that's a tricky question. But you have to know that you remove things with zero variance or near zero variance. And then you have to know that you that X5 is a linear combination. If I were to put this as a test question, I wouldn't write it like that. I would write the test question. And once again, if Alex is watching, someone could literally just screenshot this and I'd put it on the test. And we covered this on Monday's activity, like the idea of zero variance, near zero variance, and linear combos, and how we don't want to feed our model. We talked about the first step is make sure your data is clean and good to use and you're feeding it the right X's. So this would be a good test question now, and it should be pretty obvious that X5 is a linear combo of the other ones. I could try to make it more obvious by doing something like 4, 3, 2, 1, and then have this be 6, 5, 4, 3, 2. So that would hopefully make it a little bit more obvious right there. It's like, oh, this is just one more. So the variation in this one is the variation in this one. This is kind of uniformly distributed. Does that look pretty good, Alex? Doing pretty well? Take a break here. Do some afternoon office hours. I think we got it for now, but I will see everybody later. Goodbye, buddy. Goodbye, everybody. Yeah.